All right. Very good morning, everyone. Welcome to our first session in person, having our first speaker actually online. It's really an honor for me to welcome Professor Zhou. Professor Zhou is the Vice President of Nanjing University. If you remember, we already had one person from Nanjing University. We had Hanja from there. So that makes actually Professor Zhou his boss, basically, right? So if you know anything about weekly supervised learning or ensemble learning, very possibly you have come across one of Professor Zhou's books in the topic. He is really well known for his books. They are kind of Bibles in the field. Well, as Professor Han just set the bar quite high, we are expecting the boss to do and to deliver an even better talk. So Professor Zhou, whenever you're ready, take us away. Thank you.
Okay, good morning, everyone. Thank you for the general introduction. Can you hear my voice now?
Yes, all good.
So today I will present to you a topic, Learnware, small models do big. I guess you do not know Learnware, but you know in computer science we have hardware and software. So the Learnware is coined by myself almost 10 years ago. At that period, we anticipated that in the future, maybe for the machine learning area, we will have something appearing with some specific format, and we call it Learnware. So before I go into details and explain to you what is Learnware, first I will start from currently very hot topic, that is a big model. So can you see my slides? I switch the slides. Can you see? Okay, great. So now we all know that big models or large language models have achieved great success, no matter whether it's ChatGPT model, Sora model, or in China, the DeepSeek models. So as a fundamental researcher in machine learning, we are often asked about the question, how do you think about the success or unsuccessful of big models? So here are my superficial opinions. First, we think that on one hand, the industry should try to exploit the technical profits of big models because they are really useful if you use them in adequate places. But we have to pay attention to the fact that big model paradigm actually incorporated many achievements of machine learning area over the past 2 decades or even more. It's not just a simple technique. On the other hand, it can be regarded as a product that merged many achievements. And these achievements are contributed by many research groups all over the world. For example, I just list one example. Maybe many of you know that non-distillation. This is a famous, well-known technique used by various big models developed such as by DeepSeek, OpenAI. For example, for DeepSeek, the claim that they can use fewer resources to build a strong model. But why they can do that? One crucial technique here is the knowledge distillation. That is, you train a big model at first. Then from the big model, you can generate some information, some data. And then from the generated data, you can use the second model to learn from it. In this way, you can use less resource to achieve some very good, even better performance. And this technique was believed to be proposed by Professor Jeff Hinton in 2015. But actually, 11 years ago, in 2004, my group has published a paper in TKD. In that paper, we proposed such kind of approach. And we also provided a theoretical explanation to see why and when this approach will work. But unfortunately, we have not invented a fancy name such as non-distillation. We call it the twice learning. That means you will learn the task twice, then you will get a better model. But frankly speaking, the essence is the same. So this year, it's my proud to see that IEEE ICDM want to present me an award, the Research Contribution Award. This award, of course, is important, but the most important is people recognize that as early in 2004, we have already contributed to the currently known as non-distillation technique. So we can see many techniques used nowadays for building big models actually have the longer history, such as 20 years of history. But on the other hand, is big model the best solution to every task? Definitely not. Because in machine learning, I guess all of people know that we have a very well-known theorem that is a low-frequency theorem. That means if you have an algorithm or model that is superior on some task to another algorithm or model, then there must exist some other tasks on which the inferior model works better than the original superior model. That means no one model can do everything. So what we can do should to identify the adequate model for adequate tasks. So we all know that big models or natural language models are powerful, such as on text-to-text tasks, text-to-video tasks, and many so on. But we also encounter some headache issues for currently the big models. For example, I just list a few. First, we all know that if you want to have a big model, you have to collect many data and then use this data to train the model. That means you have to plan the task in advance. For example, in my plan, I will do image recognition. Then I can collect the data to build a very strong big model. Then I have a good model for image recognition. Also, I can have a good big model for financial risk control if I have already planned this task. But if I have a level consider that I want to do some tasks such as weather forecasting, then I do not have a model to use. That means you have to consider the task in advance. If you encounter a new task, then you do not have a big model in time. The second issue is the consumption of huge energy in the carbon. As everyone knows that if we continue this kind of way to develop more and more big models, then resource and energy will be unaffordable, and this is unsustainable. And also, in some tasks or application, we'll encounter some new data. We have to do some adaptation to the new environment. Then we'll encounter the so-called catastrophic forgetting. For example, suppose I have 100 T data to train a very good model, but then when I deploy the model and the model encounters some new environment, suppose the model receives some new data, the 10G data, then can we use the 10G new data to refresh, to update the original model? We could not do that. If you do that, some learned knowledge may be washed out. And more important is we do not know what knowledge have been washed out. So in order to guarantee the performance are consistently improved, we have to put the new data together with the old data to train the model together. But that will cost huge cost. So we could not do this frequently. Needless to say, we always want to have a model to do continual learning or lifelong learning. For example, we will be happy if we can have a model to learn from poker first, then learn from chess second, and then learn to drive the car. But unfortunately, we could not do that. The key component is that because currently we always use the BP algorithm to train the neural network algorithm, to train the neural network models. Well, the BP algorithms are based on the gradient derivative. Then if you want to do the derivative, you have to have the derivative objective to be fixed. If every time the objective will be changed or varied, we could not guarantee the algorithms continue to converge to the planned task. So for the neural network big model, we can hardly do lifelong learning. This is a very, very big, serious problem. And on the other hand, from the data aspect, though we are currently in the big data era, we have to notice that there are still many tasks on which we can hardly collect a huge part of high quality data. For example, oil field locating. For this kind of task, we can only get the data by induce some deep sea earthquake. So each data instance is very, very expensive. Frankly speaking, over the whole world, we only have several tens of this kind of data samples. Then you can hardly train a big model. Maybe some people will say, okay, now we can have generative artificial technique. Then how can we use the very limited data to fit to a generative AI model, then maybe they can help to generate more and more data to use. But we have to pay attention to the fact that the data information cannot be produced from real. We can have some generative data because some tasks are very correlated. Then we can use some correlated information to help the current task. If the current task, such as oil field locating, can hardly have some correlated task, then we can hardly generate useful information from scratch, from zero. So for this kind of tasks, we have to handle the situation that we have limited data to use. And another serious issue is when we use big model or large language model, we generally need to collect all the data together, then train a model. Ideally, this requires that every stakeholder will give up data for privacy. Otherwise, you can hardly collect all the data together to train a model. This is easy to do that for some entertainment application. For example, image, video, and natural language text. You can get them almost with free cost from the internet. But for some other tasks, this is very difficult. For example, for some medical treatment application, can you ask the major hospital to share their data to help some community clinics to train the model? Even if the big major hospital agrees to do that, they cannot do that, because if they share the data, the patient's privacy can hardly be guaranteed to be protected. And in some mechanical production areas, this is also the similar situation. Ideally, we want to ask the enterprise to provide their data such that we can use all the data through a big model, then use a model to improve the productivity of all these enterprises. But in practice, in reality, no enterprise agree to provide their data to us to train such kind of a cross-company model, because every company feels that the data themselves is their treasure. Then finally, we can only use the in-company data to train a model. But in many situations, the data in one company itself are not that huge, and we could not have enough data to train a big model. So overall, there are also other situations such as machine learning. For example, train a big model, we need to have many tricks. But for common user, they can hardly know these tricks. Even if how about tuning the parameters is also difficult. So common user can hardly get the performance as expert-like users. So overall, we believe that big models are more suitable to rich resource application, an application where you can train model offline, and then once get the model, you seldomly, you really want to update, and the tasks should be high frequency tasks. That means many people pay attention to the task such that you can easily to collect many data. Well, if you encounter some application with small resource, such as driving aircraft, then the computing facility, the storage facility, or even the in-time response requirements can hardly enable the use of large models. And also, some application we need to do online training, online updating. And for some very important task, a long tail task, very few people pay attention to that, but the task is very high value, it's very difficult to collect more data. And for these kind of tasks, maybe the big model or large language model are not the adequate model. We need to seek other machine learning models for these tasks. So we should not put all eggs in one basket, and we need to pay attention to other possible paradigms in parallel to the currently very hot big model paradigm. So here we come from Learnware. So what is Learnware? Now first, may I give you an analogy? Now all over the world, there are many people have built their own machine learning applications. They have built their own models. They do not want to disclose their data, but they are able to disclose or share the model. Because on one hand, currently many machine learning models are black box. So this is a shortcoming from one side because you can hardly know what have been learned. But on the other hand, this is also an advantage for sharing the model. Because sharing the black box model does not mean you have disclosed your data secrets. So many people are willing to share their model. Now suppose we have a place to accommodate these models. Now we call the place as Learnware market. Here, each knife, each hammer, each tool is an analogy to a trained machine learning model. Then what is Learnware? So we know in computer science, we have many equations, such as a program equals to data plus data structure plus algorithm. So we created equation, Learnware equals to model plus specification. Now you know that the model is a trained machine learning model. Then what is specification? The specification is something that will enable the model to be adequately identified and reused according to the requirement of future users. In other words, the specification is some kind of characterization of the functionality of a learned machine learning model. But the specification is not created by user, is not created by human. It's not a handwriting things. It's actually generated by a machine learning process. And this process will generate something characterize the functionality of a model. But the whole process does not need the disclosure of the developer's own data. So this is the most important thing. So once we have a Learnware market accommodates millions of models developed by different developers on different tasks, using different data, optimizing different objectives, then we can do many powerful things. Originally, we call this place as Learnware market, but after discuss with many colleagues, they suggested that when we call something market, this have some meaning of trading. But actually, in the future, maybe we can do some trading. For example, if some Learnware are popularly used by some future user, then we can charge some money from future user. Then we return some money to the model developer. But now we just focus on the science and technical part. So we use the term Learnware doc system. In my following presentation, I will exchangeably use these two words, Learnware doc system and Learnware market. You can understand that the Learnware doc system is some place to accommodate all the Learnwares. Now, when we have the Learnware doc system, so for a future user, when he wants to develop her own machine learning application, she does not need to collect data from scratch. She does not need to train her model from scratch. Instead, she just submits her requirement. Then once the Learnware doc system receives the requirement, the system will try to identify some Learnware. That is one model or a set of model to be assembled together, then to return to the user. Then maybe the user can use her own data to polish the model or the set of model, then her own task can be solved. So if we regard machine learning model as a tool, then we can see in the whole human history, every tool is in this kind of a situation that when you want to use a tool, you do not need to do it from scratch. For example, if I want to have a knife to cut meat, I will not go into dig the coals or build the knife factory by myself. Instead, of course, I will go to some supermarket to look for whether there's some knife for my use. And even if I could not identify a knife to cut the meat, if I can identify some knife to cut the watermelon, that's enough. I take the knife back home, use my own data to polish that, then that's ready. But nowadays, for machine learning tasks, we still need to collect data and train our model from scratch. So in the future, we believe that we will have something as Learnware enable us to use machine learning process just like we use the life. We do not need to do everything from scratch. We can build our task based on other people's results or partially from that. So the most important thing is in the whole process, the model developer does not need to disclose their data. And even for the user, does not need to disclose her data to the Learnware market. So this is the key of the whole process. The whole data, private data, are protected. But without knowing the data, the Learnware doc system need to know what model is useful for the user. Then how it can do this? The key is the specification. So we can see here, for the whole program, we need to identify or overcome two big challenges. The first is, how can we invent the specification? This is a unified form for various trained machine learning models. And the second, how can we build the Learnware doc system? It should be involvable and growable, because you can see the models will be submitted sequentially, and the later submitted models does not know what models will be submitted in the future. Then can we use the future models to help improve the characterization, the specification of the originally submitted models? So these two are the key fundamental challenges of the whole paradigm. So we proposed the idea in 2016. You know, in that year, there's no any big models. And even for the deep neural networks are just attracted many people's eyes at that time. At that time, when we proposed the idea, many colleagues believe this is just a kind of a fiction, maybe even not a scientific fiction. But after 10 years, almost 10 years, now we have almost solved all the scientific questions, problems. So before I go into technical details, first, I give you some high-level understanding of the difference of the Learnware paradigm against the classical machine learning paradigm and the big model paradigm. For the classical learning paradigm, you know, we have a task, then we build a model for that task. Well, for the big model paradigm, you know, we collect the data, and with the collected data, we train a big model. Then the model can provide a service to many, many downstream user tasks. For example, we have ChatGPT big model, then we can do any kind of a text-to-text task. For example, we have a document to have an abstract. You give a topic, and the model can write an essay, and you can have a natural language correspondence, dialogue, and so on. But all these tasks are the same category. The ChatGPT big model could not drive a car, could not play chess. Well, for the Learnware paradigm, you have many models built from private tasks. We do not collect the data. We collect the models. Then once we receive the model, we attach the specification to the model. Then it becomes a Learnware. Then once we have many Learnwares, we can provide a service to many, many tasks. But these tasks can belong to various categories. So this is easier for you to understand that, because if someone has submitted a model to be able to play chess, then of course we can play chess. If some people submit a model to drive the car, then of course we can drive the car. But I want to mention one very special property, that even if for some task, even when no people have developed a model for that, it's possible to build some new model based on the concatenation of some existing model put together to solve the task. That means even for some unplanned task, we can identify the model to put them together to solve the task. For example, I give you an analogy. Suppose no people have built a model to distinguish class A and class C, but some people have built a model to distinguish between class A and class B. Another people have submitted a model distinguish class B and class C. Then we can put these two models together. Then this new model may be able to do distinguish of class A and class C. So in other words, for some kind of unplanned task, I do not mean all unplanned tasks. I just mean for some unplanned task, it may be possible to assemble some existing model together to solve that. And it's very interesting that I want to tell you that in our own research, we found that there's one model which was developed for weather forecasting by developer. We found that it's useful for oil field identification for the oil soil property characterization. So these two tasks are with a very different target, very different feature space, very different class to be distinguished. But finally, we found that the one model can be useful for another totally different task. So this will be disclosed later. So if we have this Learnware doc system, then you can see some boring issues to currently big models may be released. Now we can use other models, so relatively data efficient, easier to get expertise, more expertise level of models. And I will mention to you later that the Learnware paradigm have a model data protection mechanism. And consider the whole Learnware doc system. Once some model have been submitted, then it will always be accommodated in the Learnware doc system. Then if we regard the Learnware doc system as a model, then it will naturally do lifelong learning. It does not forget anything. Then for some unplanned tasks, maybe by assemble some suitable model together, it can be used to solve unplanned tasks and the relatively eco-friendly. And this is a very different way from current big model. It assumes that all models are useful. And even if some people trained her own model, she feels that the model itself is not useful for herself. Maybe this model can be useful for other people. So for Learnware, the paradigm is you just submit your model. Whether it's useful or not will be judged by the Learnware doc system. The Learnware doc system maybe will feel that some model not useful for the developer may be useful for another user. Then we can accommodate the model together. And even more, if you have many, many small models in the Learnware doc system, maybe some task we currently believe only doable by big models can be doable by the ensemble of many, many small models. Of course, if some people want to submit their big model to the Learnware doc system, we still can do big and small models collaboration together. And also, there's no catastrophic forgetting and a natural lifelong learning if we regard the whole Learnware doc system as a model. And more important, the developer and the user's data are protected. And the models will be used beyond it is. That means the developer believes her model is designed for task A, but finally, the model may be used to solve task B, task C, and these tasks are beyond the expectation of the model developing herself. And philosophically, if we see the big model paradigm is a few big areas to do everything, then the Learnware paradigm is to believe the power in the crowd of people. When we have many, many crowd of models, then we can do something unimaginable and very unexpectable. So we expect that when there are hundreds, thousands of millions of models in a Learnware doc system, an impressive ability will emerge or exhibit. Now, I will go into some technical details. Because of the time, I will only focus on the key challenges for developer the Learnware. The first is what is specification? The specification should be able to represent the specialty and the utility of the model, and enable the model to be adequately identified to reuse according to the future user's requirements without disclose the developer's data. So first, let's revisit what task is doing by machine learning models from a very abstract level. For any machine learning model, suppose it's F, what it's doing is to do some mapping in a functional space from the input domain X to the output domain Y with regard to an objective. Then we can see every model doing this kind of function is put into a functional space. this functional space is a kind of we call the specification word. Then different specification word is split into different islands. Models sharing the same functional space are located in a specification island, while the models that are helpful for the tasks, for the same tasks, are put at the nearby spaces on the island. These islands originally are separated, are scattered, but when more and more models are submitted, then some islands will be merged. For example, suppose the F1 space accommodates all models of the text models. The F2 space accommodates video models. Originally, they are scattered. But now, suppose the Learnware doc system receive a multimodal model. As this model across the two spaces, both X1 and X2 are involved. Then, with this model as a bridge, we can link these two islands together. That means F1 island and F2 islands merge together. Then we can see that originally the F1 models now can be helpful for the task of models on F1 islands. That means the text models can be helpful to video tasks. So this is already beyond the identification, the expectation of the developer of F1 models. Then with more and more models are submitted, all the islands will be merged into a continent. In the continent, all the models are collected in the very general functional space. Then governing the specification word and governing the specification island actually is the same. Now we pay attention to the abstract level of understanding. Then when the developers are submit their models, actually, we just want to put the model into an adequate specification island. Then when the user submit her requirement, we use a similar technique to generate a requirement specification. And what we are doing is just to identify the right places for the requirement. Then this is a requirement. Then if we just want to identify one model to return to the user, the simplest way is to identify the most nearby model to the requirement and then return the model to the user. Then this is our specification design. The specification design involves two parts. The first part is a semantic specification. This is semantic tags to describe models type and functionality through a set of descriptive tags. Different developer of the Learnware doc system can design different sets of descriptive tags. Then the tags will locate the specification island in which the model resides. Then for each specification space, we have a statistic specification. This specification is generated by a machine learning process, and the result is to characterize the statistical information inside the model. That is, it briefly explains what kind of distribution the model should be applied. In this way, we can locate the adequate place for the model within the specification island. Now, currently, we use the RKME specification for the statistical specification. This is a very simple technique. It's based on the reduced kernel mean embedding. That means from the original data task, we will generate a reduced set representation and use the reduced set representation as the specification for the model. So the idea is very simple. For every model, you will train from the original data set. So the original data set is with the input X, output Y. And suppose there are M number of instances. Now, from the same training data, we will generate a reduced set. This reduced set have just N number of instances. The N is much, much smaller than the original M. Then this is in another very small space and a very small set of data in the small space. Then this kind of a small data representation is regarded as a description of how the model generated for the original data set can be useful. Briefly speaking, you can understand this from an abstract level. When we train a machine learning model, actually, we want to have a model capture the distribution held by the original training data. But we hope the model can do some generalization. So the model is very complicated. Now, suppose we just want to capture some information from the original data. The information just tell what distribution are captured by the model. But we do not need to have the information to have a generalization ability. We just want to use information to let us briefly know what the model is most applicable, most adequate to be used on some task. Then the reduced set can be very, very small. For example, for even the original data set, you have 10G data. Then the generalized reduced set may be just a 60K. So it's very small. Then we use it as a specification. Then how the specification is generated? I give you the plot to see. Now, this process involves two parts. One part is a model developer. One part is a Learnware doc system. First, the Learnware doc system will give two information. One is a K. The K is a function. Then the N is the size of the specification. Then I just pass the two information to the model developer. Then the model developer at her own side, she will use her own data to train the model. Suppose the model is F. And also, she will use her own data together with K and N to generate the phi theta. The phi theta is the specification. Then the model developer will submit the model F and the specification phi theta to the Learnware doc system. So you can see the whole process. During the whole process, the data is always at the model developer side. She will never disclose her data to the Learnware doc system. Or on the other one, you use some other words, the Learnware doc system never get in touch with the original data of the model developer. But maybe you will ask that because the specification is generated using the K and N given by the Learnware doc system, is it that possible for the Learnware doc system to crack my own data by using K and N and the phi theta specification? For this, well, it's able for the Learnware doc system to attack, to get developers' training data. Is it possible? Last year, we have a dual proof. That means it's very, very safe. First, the specification does not contain any original data. The second, even if for the most strongest attack in information security sense, that is the inference attack and linkage attack, these are considered as the strongest attack against the deterministic algorithm using brute force attack. Even with this kind of attack, your data is still safe. That means the Learnware doc system can never use the specification to recover the data of the model developer. So that means when the model developer submit her model and submit the specification, her data has been protected, will not be disclosed. Then, when the Learnware doc system have the specification, then what can we do when the new user submit her requirement? First, similarly, we will send the K and N to user. Then user will use her own data to generate the user task specification. Then she will submit the specification. Now, if we will just want to identify a single Learnware to use, then this is very simple. You just identify the Learnware with the smallest specification distance to reuse. But if you want to return multiple learners, then this is also simple. For example, we can do the weighted compilation. You identify several learners and do weighted compilation to return to the user. So nowadays, the very popular mixture of experts actually just is a special case of the weighted compilation. And for the Learnware paradigm, we can do some even more complicated compilation. For example, we can do chain compilation. This is what I have mentioned to you. If I want to do A and C distinguishment, I can do A and B distinguishment at first, then B and C distinguishment in the second, then put them together to resolve A and C. And we can also do tree-like ensemble. And also we can this is not ensemble, it's a tree-like ensembles. That means different model solving different part of the task. And this can be assembled together using a tree to solve the final task. So you can see we can ensemble many different models together to solve the final task. Then maybe you will also task when the user submit her own task. Suppose the Learnware doc system contains millions of tasks. Do I need to match the user requirement specification with every model in the Learnware doc system? If I can only do this, then efficiency will be too low. Fortunately, we have solved this task. We have designed the anchor Learnware. That means every time the Learnware doc system will give the user several anchor Learnwares. Then it's the user's hand. She can test whether the Learnware is useful or not. So let's look into this analogy. Suppose we just identify one Learnware. Then we can do something like a clustering to have some prototype, such as the triangles. Then we just send the prototype, the center of each cluster to the user. Suppose we send the 3 Learnware to the user. Then at the user side, she will evaluate whether these models, which one is better, which one is worse. Then she will return some statistical information. For example, the first Learnware is low, the second is high, the third is low. Then with this information, we can re-identify some Learnwares, then to send to the user. Just with several rounds of feedback, then we can identify which Learnware is really useful to the user. So in this way, we do not need to exhaustively match all the models. We just need to send several models in several rounds to the user, and the user judge which model is useful. Then finally, we can provide the user with the adequate model to use. Then, for many models, they are developed from different tasks. How can we use this model from different tasks together to solve the future user's task? Now, suppose I just give you an explanation for the most simplest tabular models. For tabular models, they are doing on some tabular data with different feature spaces. So we call them as the heterogeneous Learnwares. They have different feature space and different Learnware learning objectives. All of them are different. So the challenge here is, how can we build a unified embedding space? But building a unified embedding space generally requires auxiliary data to model the relationship of different feature spaces. Now, we do not have the auxiliary data. Then can we still enable the different model developed from different space to work together? Here we can do that because we have the specification. Every model carry on with a specification, where the specification describes on which tasks the model is most adequately to be useful. Then we can use the specification with a bridge to build a unified embedding space. No additional data are needed. No data about the co-occurrence of the models are needed. We only use the specification. Then we can build an inherently embedding space. In the inherently embedded space, we know this model, even from a very different feature space, they can be used together across the feature space. Then, specification of the heterogeneous Learnwares in the Learnware doc system can be involved, because when different models are submitted, each model carry on with specification. Then we can use this specification to calculate, to estimate whether the current model is useful on that task or not. So you can see each model, when it become a Learnware, it have a specification. This specification describes what task is the model is adequately useful. Then we can use specification to estimate whether the other model are useful for this task. Then with this situation, we can enable the specification update and evolve by exploiting not only the other Learnware specification, but also their pseudo output, then leading to the result that the more the accommodated Learnwares, the better the characterization ability of the specification. So let me show you a very general specification involvement. Now suppose originally we have a model A, then the specification originally have only the first bit. The first bit for analogy as the model's own task, suppose its error is 0. Then when the second model are submitted, we have its specification. Then we can use specification to estimate whether the model A is useful for the task 2. Then the specification increase, have the second bit to estimate whether the model A is useful for the second task. Then suppose we have a 100 models submitted. Then the specification will evolve to 100-bit length. Now we have a more clear characterization of the functionality of the Learnware. Then with the growth involved specification, we can have more clear understanding of the relation of the different models. This will provide a stronger basis for us to exploit the models together. Then when we have a long specification, maybe you will ask, okay, with a million models, you will have a million lengths of the specification, so it will be more tedious. Then we have some technique to reduce them. First, we can build some specification index. Then we can use the we can exploit the sparsity inside the specification. Then we can use some hash technique to explore the sparsity. Then finally, we can have a invulnerable Learnware doc system. So first, many models are submitted. Then when more and more models are submitted, we build the index tree and we build the hash table. Then the whole specification reduced or shrinked, then such that you can submit more models. Then with more models, the whole Learnware doc system can be growth again. Then we have more models, it will be shrink again. So I just give you another idea that I just use a tabular model as an example, but actually we can also apply to large language models. Here, the basic idea is the Learnware doc system will give a F and N to the model developer, and the model developer use F and N to build a specification submitted together with the model. When for classic machine learning model, we use a kernel function with F. For large language model, we can use a neural networks as F. And even for currently the agent software, we can also use some implicit function or reference to build specification. So in this way, we also develop the PAVE specification to large language models. So I will not go into details, just to tell you that now for the big models, we also can have a specification to enable them to be exploited in the Learnware doc system. And just several months ago, we have published one paper which shows that in the Learnware paradigm, we have several 7B models. Then their performance are comparable to 256B models. That means we have a small set of small models, but the performance even comparable to even bigger models. So we can also have a heterogeneous big model view of the Learnware doc system. If you regard the whole Learnware doc system as a big model, then it's a heterogeneous model. First, they receive some small models. When more and more models are submitted, the Learnware doc system will grow. But after grow up with the specification, the model will be reorganized. Then this in the same specification island will be shrinked. And then we can see this part a response to one specification island, response to one functionality. In this way, the different islands are responsible to different functionality. So I just have the time to give you an overall understanding. And just the two key fundamental issues. One is how to build the specification, and one is how to enable the model to be growable. The specification can be involvable. And there are many, many more techniques. And if you have interest, we have open source, the first Learnware doc system, the Beimingwu Learnware doc system. You can access it online. This system now have two functionality. First, welcome you to submit your machine learning model. Nowadays, this Learnware doc system only accommodates maybe 1,000 model. It could not provide service to business applications. So we hope more and more model can be submitted. Then with more and more models, maybe in the future, we can provide some business service. The more important is the second aspect is nowadays, we just provide some solution to the technical issues. We provide some simple solution. Welcome more researcher to come to work on the paradigm to develop your own solution. Then when you develop solution, maybe you want to have some place to run your experiments. Then you can submit your algorithm to the Learnware doc system. Then you can run your own experiments inside the system. In this way, it will help you to do research in the Learnware paradigm. Nowadays, with the big model paradigm, many people, faculty, and students in university claim that they can hardly do research anymore because they do not have the computational power. And the computational power are just, the GPUs are mostly in corporation, your companies. So you can only do research with them. But now the Learnware paradigm is just something new. And you do not need a huge computational power. You can just use one laptop. You can already do some research. But when you want to do some experiments, you can submit your algorithm, submit your invention to the open source system. Then we can help you to run the experiments. So this is a scientific research prototype. But also, if someone want to do some startup company, to do a startup company, then we'll cooperation, please feel free to contact us. We're also happy to help startup companies. Maybe some of you know Hugging Face. Hugging Face is a machine learning model pool. It just accommodates many machine learning models. It's very successful. So Hugging Face was switching to machine learning model pool in 2020. Nowadays, its value is more than 4 billion or 5 billion and accommodates more than 800,000 models. But you see, from the Learnware view, it can be viewed as a Learnware 1.0 version because it just uses natural language to describe whether the model can do anything. But you see, when you have a model, even for its developer can hardly use natural language to fully characterize whether the model can be used for something. Because, as I have mentioned, some model even can do some task beyond its expectation of its developer. Then you can hardly use NLP, natural language, to describe. The second, it only considers neural network. And when models are retrieve the user just use some natural language to retrieve the models, and there's no protection about user or developer's data. Well, the Learnware design have many things, many carefully designed. For example, we consider protect developer and user's data. We consider how to put several models together to solve the future task, we have considered how to enable a model to be used beyond the task of the original developer. So the successful of hacking phase demonstrating that the Learnware paradigm is very, very practicable and very promising. And finally, before concluding, let's think about a few questions, very high-level questions. First, in the future world of machine learning, will we use one model to solve all tasks, or have to use multiple or many models to collaborate? What is your answer? My answer is B. Our answer is B. We believe that the future world of machine learning will use multiple or many models to collaborate. We can never use just one model to solve all tasks. Then the second question, will the many models are built by one developer or built by many different developers? Our answer is also B. We believe these all models will be built by many different developers. That means different individuals or different enterprises. Then the third, now, suppose we have many developers of the models. Will these developers all over the world will publicly share their training data or not? We believe most developers will never share their data. Most of them won't share their data. So if your answer to all these three questions are also B, just like ours, then we'll encounter this situation. Given the condition that the developers won't share their training data, and even the users do not like to disclose their own data, then how to know which models among the millions of models are helpful to user task? How to reassemble models developed by different developers aiming to different tasks to work together? And how to do currently what we said, big, small models collaboration. Then, in addition to the model, we have to have something besides the model. Then, that is model plus specification is Learnware. So I believe Learnware is the future. If we believe all these questions, the answers are B. So if you have interest in this line of paradigm of the research, welcome you to join the research together, and feel free to look into these papers for details. Thank you, that's all.
Thank you. Thank you very much. Thank you very much, Professor Zhou. I think it was a really nice, a very interesting presentation with a lot of analogies that, to me at least, it was very easy to understand. Are there any questions in the room? No. Can you stand up and can hear, please? Yeah. I believe, Pedro, you also have one, right?
Okay. Yeah, but you can also. Okay. So first of all, could Professor Zhou, thanks for the talk. Could you come back to the PPT where you define the models as functions from input and output, just to check, because you put an example, a really good one.
This one?
Yeah.
Here?
Whatever you use, like, or maybe next one, because you fused even in the input space, like considering
this one?
Yeah. With the multimodality of models. Yeah.
Yes.
What do you want to do?
So this one, originally, we have many models developed for the text. They are put onto the F1 island.
Yeah.
So F1 island are models from X1 space to Y. X1 space is a text space. Then we have the F2 specification island where the models developed from the X2 space to Y.
Yeah.
So the F1 is text, X2 video. So originally, these two are very different. Now suppose we see this one model. This is a much model involving both text and video. Then we can use this model as a link, as a bridge to connect islands. Yes, this is the idea.
My question was about this merging could be like if you have a set point on X1, you from is it more related to fusing somehow both modes? Maybe it's better for you to see me like that. Related to if you have a point on the video instance, you use the second model, the second function. If you have text, you use the first function, or somehow you can share, like use both, because at first it does not.
Okay, this is understanding is F1 is not a single model. It's many models here. F2 is not a single model. There are many models here. And when we have this one task, we are not just picking one model here. We just use it to collect this set of models, the relation with this set of models. So for current task, maybe one model here and one model here collect together as a point. But maybe for the future, another thing, join in this functional space, another model of this island and another model on this island, their pair may be better. So this is not just pick one model to link with another model. They are pinning the two spaces to enable the sets of models. And this set of models know how to work together.
Okay, kind of a stacking or something like that, you mean? Yeah. Like stacking, learning, and so on.
This somehow, just you let me give abstract level understanding. You consider here are many points. Each point is a model in the functional space.
Okay.
So many points. Each point is a model in the functional space. Then you are here using this model to link. Then you know these sets and these sets, there are many links are built. This is just like a plot graph between the two functional spaces. So this is basic idea.
Now I got the things. Like I got the wrong idea. Right. Okay, thank you. Now it's clarified. So
thank you very much. You want to come here, please, Ramila? No?
Simple question. How long has Learnware been around, and what sort of growth has Learnware seen?
Sorry, come here.
Now I will repeat the question for you, Professor Zhou. So Ramila is wondering how long has been Learnware around so far?
Learnware around?
And the growth of user using your platform so far. Yeah.
Okay. We just make it publicly available last year for the platform. Then the platform just have survived less than 1 year. Oh, I'm not sure. Oh, I see. You ask how long will Learnware live in the Learnware doc system, right?
How long has it been around, basically? When did you publish it or allow people to use it?
Now you can use that.
Since when? That's the question. Since when?
Since last year.
Okay, cool. Fantastic.
Since last year.
Fantastic. There is also a question for you in the chat. If you want to read it directly, probably it's easier than for you to have a look and.
Welcome to send me email. I know the time is very precious for the winter school. Welcome to send email to me.
Okay.
Then, please.
I have just a very final question. So I was wondering if you're a final user of your platform, right? And yes. I say, well, I know very little about machine learning. I know nothing, but your platform suggests to use one model because it believes it's going to be the best model to use with my data. Because if I understood correctly, you do have specification of models, but also you use machine learning to somehow get some information from your data without basically, giving the data to the system, right? But how will you know if a fine-tuning strategy would work for that particular data? How, do you advise a user on what to do, how to do that fine tuning for their data to work with your model?
So there are two kind of users. The first kind of user, as you mentioned, maybe she know nothing about machine learning. She just want to use machine learning. And she herself even does not have the ability to tune the models. Then for this kind of user, we just send her the K and N, then she uses her own data to generate a specification, user requirement specification. Then she submits this user requirement specification to the Learnware doc system. Then the Learnware doc system will send model to her. Then she just use the model. That's okay. So this is the first type of user. The second type of user is she knows something of machine learning. She can tune the model. Then she has some data. Then she submits the specification and the Learnware doc system will send her some model. Then she can try to use the model to adapt to her own data. That means she can use the data to tune the parameter, just like tune a pre-trained model. Then for this kind of user, without the training model process, she can have a model adequately to be used. Well, different from the current big model, you have to plan everything in advance. With Learnware, you do not need to plan something. Even for something unplanned in advance, you still be able to identify some model to use. This for this second type of user, she can use it in this way.
Fantastic. Thank you. Thank you very much. I don't think there are any other questions, or yes, there is one question. Carlos, you wanna please come here? Yeah, we're in a big room with 50 people, Professor Zhou, so we only have one microphone here at the front, so it's a little bit funny situation. But we're gonna go for the last question with Carlos. There you go. You need to speak through the mic. It's a little bit but yeah, it is a bit tall for me, so yeah, it's okay. No, it's okay. It's good. So thank you for your talk. I think it was very, very interesting, and the concept that you split this match using a reference. I think it is an interesting idea. But I wonder what happened if the specialized small language model, or sorry, if the task is split in not one specialized small language model, but several language models. I mean, maybe they are too specialized and they cannot cover the entire concept of the task the user is defining, or because it is too complex or too wide. I don't know. So what do you think about that?
So I'm not sure whether I have understand the question. The question is, for some task, if it can be decomposed into subtasks for different large language models, then it's already doable in this way, right? Yeah, of course. But nowadays, what the decomposition is by people themselves. Because, for example, for a big task, a user need to know how to decompose a task into subtasks, then feed each subtask to adequate large language model. Then it's user to do the decomposition. Well, for the Learnware paradigm, what we imagine is the user just submit the task requirement. Then the Learnware doc system will have an automatic way to do the task matching or task decomposition. And compilation or reassemblation of the models can be in some complicated way, such as a tree-like way, chain-like way, and so on. But of course, not all tasks it can do. Maybe some tasks can do in this way. But for some tasks, if the user is already know how to do the decomposition the perfect way, then of course, the user can do it nowadays. But what we are paying attention to is there are something maybe the user, even the user herself, does not know how to do the right decomposition, then the Learnware paradigm can be helpful even for large language models.
Okay. So it is a task for the future, but I think it will be an interesting improvement of the of
Yeah, it's
improvement.
a way
Yeah.
to enable many models to collaborate together. And even when the user do not know which model is developed for which task, then the Learnware doc system will help her to use all these models to solve her task, to pick some sets of models to use.
Hmm. So thank you very much for your time. It was really interesting.
All right. Thank you very much once again for joining us and today on your Friday afternoon. So enjoy the rest of the weekend. And we here are going to give you a big clap. I don't know if you can hear it, but we are doing it for you. Thank you very much.
Thank you.
Bye-bye. Bye-bye. All right. Shall we have a coffee, please? Please. 30 minutes. Okay, a quarter past. Please start with Jamal.
of introduction, So we have to wait. Un poquillo, sí. He dicho que empezaría, pero que tengo que esperarte.
Sí, espérame.
Están ahí. Sí, no, pero hay un switch ahí. Yo lo tengo controlado. Yo lo tengo controlado.
Next to Pedro is fine, yeah. Thank you. All right, shall we make a start, please? Yeah, can you shut the door? You guys ready for YouTube and this stuff? You let me know, and then we make a start. All right, welcome back. So next up, we've got my very good friend Jamal Toutouh. Did I pronounce it? Yeah, I kind of.
You tried. Yeah.
I tried again. Open world. I tried to pronounce something I don't know how to pronounce. So Jamal is currently an associate professor at the University of Málaga, but he actually accomplished one of the dreams of every computer scientist. What is that? To work for MIT. He went to Boston to work for MIT, and I think he went there I imagine him working on an office without any windows, all the time working, and then coming back to Malaga and saying, yes, nice and sunshine. And that's how I see him. And Jamal is one of our experts in Coevolution, generative adversarial networks, and today he's gonna deliver to us a really great tutorial. I have very high expectations of him, so please welcome Jamal and, ask very difficult questions to him, right? That's why I brought him here. Okay, thank you. Go for it.
Thank you very much, Isaac, for your introduction. First of all, I want to say thank you to the organizers to inviting me to give this tutorial here and allow me to do maybe the hardest 100-kilometer trip ever. I needed 3 days to get Granada from Malaga. And actually, I'm not really sure about how I'm going to get back home. No trains yet, so.
You don't have to come back.
Well, I should ask my wife, maybe.
Yeah, maybe.
So thank you very much. The idea here today is to discuss a little bit how can we use Coevolution to address neural network training, focusing on this kind of multi-models neural network training. The idea here, as he said, I was at MIT. I'm affiliated at MIT. I'm still working with them. This tutorial and the work that I'm presenting here, I worked with my friends in Alpha, with Una Mayorelli, really well known in our community, in the evolutionary computation community, an amazing PI. If you have the opportunity to meet her in any kind of conference, please say hello. She's really amazing and a really friendly person. And also with Eric Hamburg, he's not in the picture, and also other people from our lab. The idea here is to discuss how can we apply, as I told you, convolution algorithms to address neural network training. As I told you, the idea here is that we have this kind of multi-models, neural network like generative adversarial networks, diffusion models, variational autoencoders, and so on. And we saw that maybe we can use what we know from evolutionary computation to address this kind of training. As I have to focus on one of the use cases, I'm going to focus on generative adversarial networks because it's where we started. And well, the idea here is that I'm going to introduce some concepts about generative modeling, then generative adversarial networks. Why do we need to use Coevolution to train them? And we will see some ideas of principles of how we applied these convolution approaches. So let's start with generative machine learning. I won't stop here, but as I want to be sure that we are in the same picture, I'm gonna do like a long trip from the basic things to maybe more complex stuff. So about machine learning, we know like we have this kind of different types of learning approaches. We have supervised learning, which is like something that we know, that we have like data sets with different features. We have like specific feature that we call label. We want to learn a function that it's able to map from some features to these labels. Then we have also unsupervised learning. Generative models focus more on this part of the types of learning where we have data. We don't have this specific label that we want to predict. In this case, we want to learn the underlying structure of the data. We want to understand better our data. And then we have this kind of semi-supervised and self-supervised learning. For example, semi-supervised learning, we want to address more or less the same problem with supervised learning. But in this case, we don't have labels for all of our data. So with some labeled data and a lot of not unlabeled data, we want to learn this mapping function that would allow us to predict the labels while in self-supervised learning. As I told you, I will focus on unsupervised learning. So we have these two really basic approaches to address unsupervised learning. We have clustering, easy. So we know the idea here is basically we want to group our data according to some kind of distance function. The idea is to minimize the distance between the groups of the samples somehow. And then we have what we call density estimation. When we address density estimation, the idea is that we have samples of data, as we can see there. And the idea at the end of the day is to get the probability distribution that represents our data. So we have like to address there are different types of approaches and steps to do this. And when we talk about generative modeling, the idea is to address this kind of unsupervised learning approach. So the idea here is that when we address generative modeling, we have a training data set, as I told you before, and we want to get the probability distribution. So the idea is that we have a data set that is represented by a probability distribution that we don't know, because most of the time it's really difficult to, because we have images, for example, it's difficult to define this kind of probability distribution. And we want to learn a model that when we sample from this model, we get a sample that belongs to the same distribution that P data of X. So that at the end of the day, we want to learn this model. We are not, in this case, we are not learning, as we said in supervised learning, a function that maps an input to an output. Here, the idea is to learn a model that when we sample from that model, we get a sample of our training data set. Why we do that? As I told you, first of all, it allows us to better understand our data. The second one, I think that's also really, really important, is that allow us to have a model that represents the whole data set. So when we are we have a data set with a bunch of images, thousands and thousands of images, it's, let's say, cheaper to store a model that allows us to create these images than storing the whole data. And actually, it allows us, with this kind of representation, we can even to keep the privacy of the data and so on. And the last, and why we are here, is because it allows us to produce new samples. Here we have the example of images, but when we talk about new samples, we can, I saw with some students here that I have a time series data, you have tabular data, you have physics simulations, and so on. So how can we address this generative modeling? So we have two ways of addressing density estimation. The first one is the hardest one, the one that I won't be able to do it, is the explicit density estimation. Basically, is that we have the data, we have our samples, and we do the maths to get our density estimation, or probability density function. So the idea is that we have like two main ways to do it. Is with, as I told you, with probability density functions or cumulative distribution functions. So the idea is basically to do the math and define and solve our P model of X. Well, when you have like 1 dimension, 2, 3, 4 dimensions, it's not that hard. But when we have images, we cannot do that. So instead of doing it explicitly, we can do it implicitly. So the idea here is to use a neural network. As we know, we can use a neural network to define any kind of nonlinear function. So the idea is to learn this neural network that allow us that sampling from this neural network, P model of X, we will be able to get samples that, as I told you before, belong to our training data set. Here you have like a really old picture where we have like the main approaches that we used to use to do that. We have generative adversarial networks, we have variational autoencoders, and we have diffusion models. As you can see here, well, diffusion models that can be also trained like a one model, but variational autoencoders and generative adversarial networks, they have like two neural networks, two models that train together to address this generative modeling. So after this introduction, boring introduction, I'm going to talk a little bit also about GANs. Basically, the idea is to learn a model, a neural network, to train a neural network that has an input. As I told you before, the idea is to sample from this model. So how can we sample from that model? Basically, we sample from something really simple, what we call latent space, a normal distribution as an input. And the idea is that sampling from this normal distribution, from this latent space, we get the output, and the idea the output should be like a synthetic sample, a generated sample, that, as I told you, should follow the same they should follow the same distribution as the real data. So if we know, as I told you, I know that we are here, we are like really smart PhD students, researchers, and so on. We know about supervised learning. So the idea here was, how can we train this generator using supervised learning? Could we try to train that? Do we have a ground truth? Because when you want to train something using supervised learning, you have the ground truth, the labels that you want to learn, you have the input, the output, and then you compare this input and the output and what you expected, you compute the loss and update the weights, the parameters of our network. We cannot do that here. We don't have a ground truth. Because imagine if we are like here, we want to generate these faces, human faces. You cannot compare the face that you are generating against all the faces there. So how we do that, the idea here is that we will use another neural network, another model that guide the training of the generator. We call it a discriminator. So here the idea is that we have two neural networks that define an arms race during the training. They apply what we call adversarial learning. They have different objectives during the training. And as you see here, the idea here is the discriminator during the training process tries to distinguish between real data that comes from the training data set, X, and the synthetic data produced by the generator. So let's say it could be seen more or less as a binary classifier, true data or fake data. And the generator learns, during the training, learns how to fool the discriminator. The generator trained to create such a realistic information, such a realistic data, that for the discriminator is not possible to distinguish between real and fake data. How they do that? Basically, we have here like an example that I will show you after drinking some water. I haven't said that before. Maybe it's not the best thing for the organizers. I don't mind. If someone wants to interrupt me, no, I'm just joking. But if someone wants to interrupt me, just raise your hand. Jamal, this is boring, or Jamal, I have a question. And maybe I can just repeat the question here for the YouTube or wherever, and we can continue. Okay, guys and girls? So here the idea is that, as I told you, we have the latent space, basically like a normal distribution. We have the training data, in this case like is images of horses, and we want to learn how to create horse images. So when we start the training, the generator, of course, has not learned anything, so at the beginning it just creates noise. The discriminator gets information data from the training data set and also data from the generator, and learns how to distinguish between this data. It updates its weights according to the loss function, binary cross entropy, for example. Then we train the generator. How we train the generator? Basically, it could produce another image, or we can use the same that we used before. And then the idea is to see how was for him, how was the score of fooling the discriminator. So how was the discriminator classifying this image as real? And that's how it computes the loss. And we use this information to update the weights of the generator. So at the beginning, the generator loss is high. The discriminator loss normally is like smaller. We train again. Of course, the generator already learned something. He was able to produce something like a horse. At this point, maybe for the discriminator, it starts to be like harder to distinguish between real and fake data. It updates the weights. The generator is learning slowly. He's creating something similar to a horse. And it's fooling the discriminator. So more or less the generator knows how to move the parameters, to change the parameters to produce more realistic data. So at some point the losses, like the dynamics of the losses start to change. So at some point, updating the weights of the generator, we are able to produce such a realistic samples that for the discriminator is not possible to distinguish between real and fake data. So at the end of the day, the probability of being real, any sample, the sample from the real data or sample from the generated by the generator is the same. So this could be like what we call in this kind of min-max optimization problems, the equilibrium. So how they do that, we can see like a little bit more formal. We have here defined the min-max optimization problem that defines the losses that we use to update the parameters of the discriminator and the generator. The idea is that here the discriminator tries to maximize the probability of classifying real data as real and minimize the probability of classifying fake data, synthetic data as real. That's why he's minimizing this part of the function. When we train the generator, basically here we have like the min-max. We try to maximize the probability of classifying real data as real. Okay, that's how we define this problem. And that's actually what it makes it hard to address this optimization problem by using SGD for some cases. We'll see later. But here we have the algorithm, the official one, the idea of you train one network and then you train the other. As you can see here, just a curiosity, They are using the same laws, okay? But here he's ascending the gradient, and here's descending the gradient, okay? That's why they have like opposite objectives in the optimization problem. So why we do use this? Because we can create samples of images for any kind of application. As I told you, time series, tabular data. We have used also this information to do fluid mechanics simulation, which actually is a pretty nice application because it allowed us to save a lot of time of simulations in physics, climate data problems, create molecules, and so on. But here we have the bad news. So it seems great. We are able to learn the probability density function. We're able to produce such a nice samples, but it's not as easy as I told you. Normally, when we deal with real-world problems, we have different types of training pathologies that make us to hyperparameterize the models, try different types of loss functions, architectures, and so on. So the well-known pathologies with GANs are the non-convergence. The idea, when I show you the example, I show you an amazing animation with horses, and we showed how the loss was perfect, and at some point it converged to some kind of equilibrium, but it doesn't happen that often. So most of the time you can have that non-convergence, is that the dynamics of the parameters, when we are updating the parameters of our networks, make the parameters to oscillate and never converge. So we don't know when to stop or how to stop. Let's say for me, maybe the most important problem of GANs, and actually when we address real world problems, it's like one of the ones that industry, when they try to use GANs for their problems they used to have, is that the mode collapse. As I told you before, in basic GANs, you have the feedback of the discriminator that give us the feedback about how good is a sample, how realistic it is. But what's the problem is that it gives you the information about how good is the sample, but we don't know about the distribution of the whole data set that you are producing. So it could produce that generative model. Imagine that we have this real world data distribution in blue. It could happen that we learn basically to produce a subset of our data set, a subset of our probability density function as a sub-area. So we can create really good samples, but not representing the whole diversity of our data set, which actually are really a big problem. And also, as in other machine learning approaches, we can have diminished gradient problems. If you have a discriminator that becomes too strong at the beginning, it won't allow you to learn anything. It won't allow the generator to learn anything, because when the generator tries to learn anything, the losses that it gets, they are really big, they are high, and more or less, let's say that the parameters move in a random way, trying to find the best way to optimize, but it's not helpful. There are like different types of remedies to do that. As in other machine learning and deep learning approaches, we can apply these different types of regularization. Okay? So one of the, actually the interesting thing is that most of the approaches, regularization approaches, work on the discriminator, because at the end of the day, the discriminator is the one that rules the training process. It's the one that's like giving us the way of how to optimize the parameters of our neural network. One of the things that I really like at the beginning is the unrolled GANs. Basically, the idea is that it's easier for you to learn from different discriminators. It's like, imagine that you are learning to play football or play tennis. If you have the only one trainer during all your lifetime, you will learn to play tennis as this trainer is teaching you. But if you want to learn to play tennis properly, the nice thing is to have like different trainers Here is more or less the same, but here, instead of having different discriminators, basically we have the same discriminator, but in different time periods of the training process. So we train the generator, and the loss that we get is some kind of an addition of the discriminator of different epochs, previous epochs, and the discriminator in this epoch. And the people that works also in GANs, they have used Wasserstein loss GAN and also different min-max losses to try to address these problems. No questions? Oh, smart people. You want to do a question?
Yeah.
Please.
But it was from a slide before.
Here?
Previous one. The one where you described the architecture of the. Yeah, for example. I wonder in the training process how you generate the latent space, because it seems like an input to the model. In the adversarial network, generative neural networks, I usually visualize it like there is a feature extractor from the image, like I'm not encoder, but I look at the discriminator. But there you didn't have this part of the autoencoder, just the generator. And so I wonder how you set the latent space as an input, how you build the latent space.
Well, I think I got your question. Your question basically is like how we can define the latent space to create images with a given features. So, okay, here I'm just discussing and teaching. I'm going to show you later. But here I'm just showing the basic GAN. So we are not using a conditional GAN. We are basically producing randomly samples. So the latent space here is a random distribution. We don't have any type of information of our, we are not getting any kind of information from our latent space. So we use this random distribution to train our weights in a way that anytime we sample any random input from our latent space, we are going to get a sample, but we don't know what kind of sample. In this case, it's unsupervised GAN. We don't have, like, let's say, label data to create some specific class of data. You're talking about what we call conditional GANs, that you have an input. You will say later, but thank you. I was able to rest, because it makes it easier for me. Well, so we have GANs, and I won't stop here. We have GANs with CNNs, and that's what you were discussing. Look at me, look at me. No, it's okay, it's okay, just kidding, just kidding, just kidding. So something that you say is that how we define our latent space to produce these samples. The idea here is that we add to our latent space input other type of information that could be a representation of an image. I don't know if you have like any kind of encoder or whatever. Before here, you encode your image, and you get the input, and then you train the GAN. It's more or less the same thing. Okay? And as you see, the problem is exactly the same, just we have just an input. Okay, and I'm gonna just to tell you this because we are gonna see some results later. So what can we evaluate our generative models? It's not easy. Because we cannot rely in our losses, in the losses, because as you said before, as you saw before, the loss of the generator depends on the discriminator. So how good is the discriminator distinguishing the real data and the generated data? And also the loss of the discriminator depends on how good is the generator producing the generated data. So we cannot rely, as in other problems, when we are working in our papers and we want to see to show how good our approach is, we show how the loss evolved. Here we cannot use the loss as a performance metric. Well, we can use people, for example, for images or for tabular data and so on. We are good at saying like images, say, oh, this is like realistic, this is not realistic. This tabular data seems that this tabular data really seems that it shows some kind of credit card fraud or whatever. But of course, as just one person cannot evaluate the whole distribution of the data. So what we do, basically we use a pre-trained model or neural network or machine learning approach. In this, most of the metrics use inception for images, use inception neural network. And basically we get some kind of statistics from the distribution, from the data, from the samples to evaluate the images, the distributions. The most known ones are inception score, that basically computes the conditional marginal Levy distributions of our samples. So the idea is that the inception scores give us an idea of how realistic or good are the samples. The problem with inception score is that it's not that good to detect this kind of pathologies like mode collapse, because it evaluates basically the samples, the quality of the samples, but not really the whole distribution of the data. And then also we have FID score. In this case, we get also some, we use the output of the neural network to define some multivariate Gaussian distributions of the real data and the generated data. And we compare these Gaussian distributions using Wasserstein 2 distance. Here the idea is that they are better in terms that it's able to compare between the two distributions in terms of quality and also the diversity, but it's not perfect in terms of diversity, but it's better than inception score. The idea here in inception score is that the higher the better. FID score, it's a distance, so the lower the better. So now the new things, I hope. So let's talk about coevolution and spatial coevolution. Actually, this is the how we evolve our neural networks. Is here we are here. We have here experts in evolutionary computation. No, it's not that fancy topic anymore. What we have there, that's he's looking at his cell phone now. Well, so let's talk a little bit about evolutionary computation. The idea here is we define computational models to address optimization and research problems, trying to mimic biological evolution. The idea here is to have a bunch of what could be solutions of our problem. We call it a population of solutions. And then we apply a principle of evolution to evolve these solutions towards the optimal of our problem, if we have an optimal. And what are these principles? We apply what we call natural selection. This natural selection is done according to the quality of the solution. We will call it fitness of the solution. How good are the solutions addressing the individuals, the solution addressing the problem. Then we apply reproduction, the idea of mixing somehow the solutions in our population to produce new generations of solutions. In this case, we will use, normally we use like two types of operators. Recombination that uses information, genetic information from two individuals. And after that, we mutate the solution. So we need one solution will change a little bit to produce the new individuals, the offspring. And after generation, we will keep in our population the good solution. I'm going to show you with an example. Oh, I haven't said that at the beginning. I have a GitHub repo with several codes about what I'm showing, examples I'm showing you here. The nice thing is that the repo is in the first slide, but here you have like a collab also Colin notebook if you want to play a little bit with these toy problems. So this is like a really well-known problem, optimization problem. It's the one max problem. The idea is that we have a bit string, and we want to get the optimum bit string, which is the one that has only ones in our bit string. So we will work with a population of bit strings. In order to talk in terms of evolutionary computation language, I will tell you that this one this one component of the vector, each one component of the vector we call gene. All of them together we call them a chromosome. When we have a bunch of them, we will call them population. Actually, this chromosome will have what we call a phenotype, but we won't talk here. And this optimization problem, the idea is that we want to maximize the number of ones, so the fitness function is really easy. Basically, we do the addition of our bit string, and it's a maximization problem, so we want to maximize this function. So let's say how we would address this problem using a genetic algorithm, a basic evolutionary algorithm. Imagine that this is what we call the search space. So all possible bit strings that we can create. So at the beginning, we basically create an initial population. Could be like randomly or using any kind of strategy. In this case, randomly. This population is evaluated somehow. So in this case, we apply this fitness function. We get the fitness values. And then we select what could be the parents of our next generation. Normally, we should add some kind of variation. So we cannot use stochastic methods because we can collapse early to local optima. So the idea here is we do what we call tournament selection. We have roulette wheel. We have different type of non-deterministic selection approaches. The idea is that you select randomly a number of solutions of our population, in this case 2, and then we select among them the best ones, okay, according to the fitness. So in this case, we have selected these 2 green ones. Here we have the parents. Then we apply the variation. So let's first do the crossover operation. In this case, there are like gazillions of operators. This is the most basic one. We call it one-point crossover. The idea is we select randomly a position in the vector, and we exchange the information from this point. And we are able to create 2 new samples. And then we could also apply a mutation. So after having this offspring, we can, in this case, we apply a bit flip. The idea is to select randomly a position in the vector and changing the bit. So if we have 1s, we change to 0 and 0s to 1s. And then we include these new solutions to our population, and we replace the individuals in the population, so we keep the best ones in the population for the next generation. In this case, I'm using a very simple elitist approach to do replacement. Basically, we select the worst individuals in our population and we remove them. And the idea here is that, well, this is that using this evolutionary approach, I have another result. You are able to move the whole population from random positions towards to the optima. Okay? So let's talk about coevolution. So it's nice because in computer science we used to say, like, easy. With our evolutionary algorithms, we're mimicking nature and so on. But in reality, when we evolved in biology, we haven't evolved in isolation. So we are in an environment, we share the environment and space and the time with other species, and somehow we interact with them. I can give it to you guys. So in nature, we don't evolve in isolation. So in nature we have coevolution, different species that share the space, the environment, the time, have an impact, an effect to each other. In nature, we have two different types of interaction. We can have like positive effect, as we see in nature, like in symbiosis and also mutualism. For example, bees and flowers. They have evolved in a way that they allow to each other to improve. So it's a positive way of interaction. And then we have the negative effect. Let's say that the negative effect is that human against nature. So human, in any case, it has a negative effect in nature. When I talk about negative effect, we talk about predator-prey relationships and also parasitism. Can you see this picture? What is the predator here? Eh? Flower? The flower? No.
The parasite.
Yeah, he saw it, but he doesn't know the name. Vamos.
Maldita sea.
Dun, 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 dun. The spider. So here we can see that a spider has evolved in a way that has the same color than the flower, and he's able to hunt the insects that goes to the flower. In general, the people doesn't see so you did great. So even you didn't know the name, you did great. So the idea here is that, okay, we saw that in nature, so we define also algorithms that mimic this behavior. And the idea that we use them when a single individual is not able to represent the whole problem, or it doesn't represent it in a way that it allows us to address the problem. So in this case, before, in an example that we saw before, in the 1 max, the fitness function basically we took the chromosome and we did an addition of the bits and we have like the fitness value. In this case, the fitness value, it doesn't depend just on one species and one population. We would have like different populations, and the fitness values would depend on the interaction of these two populations. This makes it harder because the fitness value now are not depend on the time and depend on the individual that you are interacting with. So imagine that we're talking about sports. I'm a crazy Barcelona fan, so it's not the same when you see Barcelona playing against Albacete. Well, it was like against a really bad team, or Barcelona against Madrid, which is not a good team anymore. But you know, the result, the fitness in this case depends on with whom you are evaluating with. And it's not the same Barcelona this year than when Xavi was with us and we were losing all the time. So that's why it's also dynamic, depends on the time also. So when we have like two different population structures, we can do coevolution using just one population, which is a little bit weird, but there are approaches that work well. So the idea is that in one individual, you define the two populations. So you have like two chromosomes concatenated, and you can apply the same operators that we saw before. So that here the members have two roles, the predator and the prey, for example. And we work, I think that, of course, we work on that, so I think that is the best way to do it. we use multi-population. In this case, instead of having just one population of individuals, we will have like several populations, depends on the problem. They apply their own evolutionary approach, and at some point, they interact, like in nature. So we will have two types of algorithms. We will have competitive and collaborative, cooperative coevolution. When we talk about cooperative coevolution, basically we have a problem in which the representation of a solution will be represented with several chromosomes of different populations, and we will evolve them. Sometimes we can evolve them in isolation. In cooperative coevolution, you can do it also with not that isolated way. And the fitness function is evaluated how well they cooperate. Example typicals of how where you can use cooperative coevolution. Imagine that you want to define a neural network. You can have a population of the hyperparameters of the network, learning rate, number of epochs, batch size, anything. And another population could be the representation of the architecture. So you can evolve the architectures, you can evolve the hyperparameters. At some point, you want to evaluate the individual. Basically, you put them together, you train the network, and you can get the performance of these two individuals. Also, you can usually see this in different domains. We have been working, I work also in smart cities problems. So we evolved the location of the bus stations as a one individual, and also the schedule of the buses. So at some point, we have these two individuals working together to get the best location of the buses and the best schedule to get the best performance of our bus public transportation. But today here we're going to be focusing on competitive coevolution. Here we can see basically a basic evolutionary algorithm. We have one population, we initialize the population, we evaluate them, we select the parents, we evaluate them, and we replace in the population and so on. So how it's the competitive coevolution? So basically, you have two populations that they apply their own operators, evolutionary operators, and at some point, we evaluate them in terms of how bad they're doing to the other one. So it's like an adversarial fitness value, like we saw in GANs. We have this kind of min-max. We use a lot, and we can see this a lot in game theory. We have used these approaches for cybersec. At some point, you can evolve attacks, and you evolve the defense strategies, and you can get like what we say robust defenses. Also in software engineering, you evolve the programs. You evolve also the tests of the program to get the most robust programs and so on. Something important here is how we evaluate the individuals, because there are like several strategies. Let's say the simplest one is that it's okay, really. For me, it's like a way to rest. So we have like, it's important to see how to select the way we evaluate individuals, because you can, let's say the cheapest way to do it is to evaluate one individual against one. What's the issue of that? Is that you don't really get how good is the solution in a really robust way, because you don't know how is the performance, because it depends a lot on, as we said before, it's really relative in terms considering the opponent. Let's say the best or the more accurate way could be all against all, but it could be expensive, because imagine that you are like in neural network approach or whatever, you have to train something, and and so on. So normally you have to select a way. There are different strategies. Another collab that you can see later, we have this binary bilinear optimization problem. It's an adversarial problem in which we used to learn a lot of the dynamics in competitive coevolution. I won't stop here, but basically we have, you can see here the fitness values of one individual and one population and the others, and you can see that it's totally adversarial. So in this case, we have an equilibrium which actually it's really hard to get. And really, so you have the code and you can play around and see, depending on the size of the population, number of epochs, probabilities of applying variations and so on. You can see how they interact and the results. So why I told you all of this and why we are here? Because also competitive coevolution have more or less the same limitation that we saw in GANs. We can have loss of genetic information. This could happen that we have a population that learns how to defeat the other one, and at some point they can, because of the variation of or how the population evolves, or how the population is losing diversity, this other population is able to learn how to defeat the other one, and they're like, but basically what we saw in the losses in the GANs could happen here. We can have like the focusing. The idea is more or less the same that we saw in mode collapse. You can have a population that learns how to defeat specific individuals in the population. This could happen in nature. You have in nature that maybe in an area. Also, why is a problem? Because in nature you can have wolves in a place that they learn through the generations that to hunt any type of animals, they should go to the lake at the time that they are drinking water. So okay, these wolves are able to eat. We have the animals that they go to the lake and so on. But at some point, maybe you have like dry season, and the lake disappears. These wolves, they don't know how to hunt anymore. They could disappear somehow. And also could happen here also in nature, and happens also in nature, is that one population could become too strong or too big. They hunt the other species, and at some point the other species disappears. And of course, this point again, we have an issue. So the other population passes away. So why we use, so okay, you have Jamal, you have more or less the same issue. So what are you giving us? Well, the idea here is that we have been working in coevolutionary algorithms maybe for the last 40 years. So we have studied a lot how to address this problem, these issues. And we saw that most of these issues can be addressed by keeping diversity in our population. So the idea is that we have to have diverse population enough to keep to have novelty each generation. But of course, you don't want to diverge. You don't want to have like a random population all the time. So the idea is that the population should be a source of novelty through the generations. And how we do that, and how we already showed that it works pretty well. Basically, instead of having two populations evolving together, we try to separate. So one of the population is separated in several subpopulations. The other one is separated in several subpopulations, and they evolve in a separate way. Okay, the idea is that they evolve in a separate way. There are two types of separation, mostly. One is spatial separation. Basically, you put them in another space, subspace of the search space, and then you keep them there, okay, evolving. And you have also what we call temporal segregation. The idea is that you have some individuals that are in a specific time in the evolutionary process, and you have another individuals in another time. This is really similar that they try to do it in rolled GANs, okay, different times. So how does it work? It works in nature. So here we have two animals, but they are like, this is the ancestor of the wolves. So we have Cynodesmus, which are wolves or dogs between 50 and 30,000 years ago. And here we have the Russian gray wolf, which is like 80 kilos of amazing predator, able to hunt and to do crazy things. And why are they different? Because 50,000 years of difference. And then you have Rita. Actually, they share the time together, but she's like a friendly, lovely 4 kilos of white-haired Dachshund. I love her, she's my dog. So this slide is just an excuse to show off my dog. But the thing is the same. So the thing is that they have like separated, they are separated geographically, so in the topology they are separated, and they evolve in a separate way. They have the same ancestor. But of course I couldn't have this at my home. I have that one. So, okay, we have this in nature. How we do that in evolutionary computation? Basically, we define a topology and we do what we call cellular evolutionary algorithms, or especially distributed coevolutionary algorithms. That basically we set up a topology. In this case, it's a toroidal two-dimensional grid, and you set subpopulation in each one of the cells, and you define a way of interaction between the cells. So we can define like a neighborhood here. And the idea is that given a cell, you will be able to interact just with the neighborhood cells. So we will be able to have, that's why we are not talking about isolation. So before here we have like, let's say isolated, they were totally isolated. Here we have semi-isolation. So at some point we will have migration, like in nature. So the individuals will move, okay, through this toroidal grid. And well, the nice thing of this toroidal grid is that when I showed you before, I told you it's important to select the way to evaluate in adversarial learning approaches. Because if you do 1 against 1, it really depends on the individual that you selected to evaluate your fitness. If you do all against all, you have n squared complexity. The idea is that when you use this kind of toroidal grid and you evaluate your population also only against the neighbors and the individuals in your subpopulation, the complexity really decreases. Depends on the size of the neighborhood. So now let's go to the coevolution and GANs. So reminding, GANs are two-player min-max optimization problem. You have the generator against the discriminator. We saw that in coevolution we addressed similar issues, and let's say we learn how to address the similar issues. So the idea here is to use competitive or cooperative coevolution as main framework to train GANs. Evolutionary computation, we have several approaches in evolutionary computation to train GANs and multimodals. I'm going to be fast here. We have what we call evolutionary GAN, which was the first approach that we saw that they applied evolutionary computation here. It's a really well-known researcher, Zhou. Basically, instead of having like coevolution, they have just an evolutionary algorithm that they have a population of generators. They train a population of generators against one discriminator, and according to the fitness values, the variation operator here is the loss. Okay, and they basically evolve the generators. They have also multi-objective AGAN. Basically, Here they use the loss to select the best individuals. Here they use a metric that evaluates the quality and the diversity and keeps the ones that are in the Pareto front. Okay, fitness of diversity and quality. Well, I have thousands, so I'm not stopping here. From our friends from Coimbra, we have Coegan. They define the GAN training as a coevolutionary approach, but they apply it as a cooperative coevolution. So the idea, they define two populations of neural networks, one population of generators, one of the discriminators, but they address the training or the population. The individuals are evaluated not according to the loss. They use a quality metric, for example, inception score, to decide which individuals are the good ones and the bad ones. So the idea here is that basically they use it as a cooperative. They see it as a cooperative way, and what way they do? They don't really train the neural networks. They basically do NAS, neural architecture search, with two populations, and they address it in a cooperative way. So the thing is that they evolve the architectures, they train the architectures, they get the inception score, and they keep the good ones. Well, in this case, they use the FID score, sorry. So our approach, Lipizzaner. Lipizzaner is a type of horse, and my PI, okay, please.
I didn't understand what is the population in this evolutionary algorithm. I mean, it is the architecture, the weight of the architecture. What are you?
Architectures. They evolved architectures. I want to evaluate my architectures. I train the architectures. So I get the weights already. I compute the FID score. This is my fitness function. That's it. So they are not training using a coevolutionary approach. They are doing NAS in neural architecture search in a coevolutionary way. Thank you.
Another question, how do you represent the architectures? How, you know?
This is not my approach. Just kidding. No, I don't really remember. So they are really good friends of mine. Actually, Pedro knows them pretty well. But I don't remember. But you have a chromosome that represents the number of layers, type of layers, maybe the activation functions, and so on. So like NAS problem, and do like in two populations.
They just penalize the solution when the crossover, for example, doesn't fit.
Oh, I have no idea. Great question. So I don't really know if they have any kind of reparation operator.
Okay.
But good question. To ask them. No, thank you. Just kidding. So the thing is that they do NAS and they evaluate in a cooperative coevolution way, coevolutionary way. So Lipizzaner. So here I have again a source code, a Colab notebook. Actually, it's a tiny example of Lipizzaner. So the idea here is that we have discriminators, we have generators. So we address it in a semi-isolation way. So we create different islands with copies of our initial population. We will co-evolve them, I'm going to show you later. And at some point, we migrate individuals from one island to the other. Basically, because this migration allows us to get some novelty from other populations. The idea of, remember that we need to keep diversity, and a way to keep diversity is to getting individuals from other subpopulations. So here's how really we do it. So instead of having like one GAN, one generator, one discriminator, we have a population of them. And as I showed you before, we define a topological grid, a toroidal grid. In each one of the cells of the grid, we locate one generator and one discriminator. And we will apply in each one of the cells a competitive coevolution training approach. So we separate the generators, we define a neighborhood, we studied what is the impact of the size of the neighborhood and so on. We saw that this von Neumann neighborhood works pretty well. So in each one of the cells, in parallel, that one of the nice things of applying a special coevolution approach is that it allows us to do everything in parallel. And actually, when we train this, as we have like population of neural networks that they could be big, we train one subpopulation maybe in the US in our slums computer, and one in Málaga, and one Sunday at some point they interact. So we have this subpopulation, and we apply a training approach that is really, really simple. So at the beginning, we have just one generator and one discriminator. We bring from our neighborhood the copy of the best cell. In this case, at the beginning, we have one just GAN, so we copy one individual. We bring them, so we have our subpopulation. Then, given, this is important because this could be like also heavy, we select a subset of batches of our training data set to get the losses of the generator and the discriminator. We do all against all. Then we perform selection. We apply tournament selection. We get the best generator and the selected generator and the selected discriminator. Our variational operator, and it's something that in evolutionary computation community they don't like because it's the SGD. They don't see it like a mutation operator properly. So we apply SGD, so we train the GAN for one training epoch. So we have updated this GAN, should be better, our generator and our discriminator. And we replace we do some kind of replacement in our subpopulations. So, as I told you, the same thing is happening in each cell of our toroidal grid. As I told you, it's really nice because we have like this spatial separation, but also we have temporal separation because when you have a computer in Málaga, a GPU in Málaga, and you have a GPU in the US, and you have, actually I'm using also GPUs in Uruguay because I have colleagues there, and Argentina, they evolve in, like let's say, with different speeds, because one GPU is like NVIDIA V100 and the other one is something else. So you have spatial separation and also temporal segregation, okay? Because we apply asynchronous parallelism, so we don't wait to the others to update, you know. So we apply this, and again we get the neighbors, and we apply this loop again and again and again. And at some point, we stop according to a given next criteria, and after that you have subpopulation of generators and subpopulation of discriminators in each cell. So what is the output of our approach? Well, as we are EC community, we like to apply evolutionary in any place. We also are, we update our learning rate applying an EC strategy, whatever. But what is the output of our approach? It's a generative model, which is defined as an ensemble of generators. Okay? So then, again, we are EC. We are always looking for excuses to apply new EC approaches, evolution computation approaches. So our generative model is defined by a subpopulation of generators, and we apply what we call mixture weights that define how we apply the generators to produce the samples in our distribution. And these weights are also optimized using a genetic algorithm. Well, in order to finish this part, we have two populations in a spatial grid. Again, it's important that we apply asynchronous parallelism, not just because it could be faster, is that we also have temporal segregation. We have ensemble of generators that are evolved, and also we evolved the learning rate. So some of the results that are pretty cool in our approach is that we are able to address vanishing gradient. Here is a simulation of one training approach in which we enforce at a given epoch, in epoch 50, we include a really strong discriminator and a really weak generator in one cell. But again, as we are getting information from the other cells, even we have like vanishing gradient in this cell, and we are applying this selection and replacement approach that it's stochastic, we don't get always the best ones, we were able to, well, here the lighter the better. In just 6 epochs, we were able to escape from this vanishing gradient in this cell. Well, we observed that we are like faster, we converge faster in a really smoother way. Again, we try to use, of course, we compare against parallel GAN training with also other kind of special separated GANs without migration. As we were talking yesterday, we did this kind of ablation study to see that our approach was providing better and better results. For example, here when you don't have migration, even you have subpopulation of generators training in a coevolutionary way, okay, they are converging, but as they are not sharing information among the cells, this is like no communication, this is with communication. We can see that the whole cell is evolving, and actually the whole cell is evolving to better results because, again, the important thing here is to have a source of novelty from the other cells. And as we increase the size of our populations, and which means the size of the grids, we get better and better results. Okay, so the size is important because the higher the population, let's say the higher the diversity. But it's true that at some point, if you have like huge populations, well, first of all, you need a lot of computation power. And also you can have the divergence because they are able to communicate because you need different steps to communicate information from this cell to this cell to have this kind of the communication to the. Something that also it's important here is that as our generators are trained in a different way, imagine that we have like collapses in our generators. As our generative model, it's an ensemble of them, we are able to combine all of them to escape from also mode collapses. This is an extreme case. If we are not thinking about extreme cases, here we have an example comparing ensemble of generators or just one of the generators in our population. We can see that we have higher diversity and better quality. This is a diversity metric, total variation distance. The lower the better. Well, and again, as we are using asynchronous parallelism, we are not waiting. So even we increase the number of the individuals and we are not waiting for the others, the computational time, it doesn't decrease that much. The problem is the memory. We need more and more GPUs. We were able to run this in Summit in the US, in Picasso in Málaga, AWS. And so as I told you, faster, better. Of course, it's my thing, so I should say that just good things about it. So this is like a picture that we are working still on it because we want to explain this in a paper. Well, we have several papers, but we want to explain this kind of multimodal training with multipopulation approaches. So we have here this picture. Imagine that you have 2 neural networks, okay? And this is the search space of the parameter space. The thing is that when you have a single or multiple neural networks, even they share space, you can move just one step each time through the search space, and well, with HDD, so just one movement in one given direction. When you have like one population of neural networks, so the parameters are defined by one population, the nice thing is that you can apply crossover or whatever, and you can escape from, you were here and maybe you apply crossover and you start here. So I think is that you can move faster and different ways through the parameter space. And when we have multi-population, our parameters can be defined with theta and theta. And the thing is that here, when we separate our parameters, imagine the GAN, we have separated the parameters of the generator and the discriminator, we can move smoothly because each one of the individuals in our population will give us a different smoother movement. That's why it allows us to converge to better parameters, to better solutions. Well, some results. Again, we saw that the importance here was to keep diversity. We evaluated how is the performance if we use different losses in different cells. So in each cell, we are optimizing towards different objectives. And we saw that we were able, as we are keeping diversity in our population, we were able to get more robust results. Something really cool, and a result is that we were able to see two main things. That we were able to prove that we were doing signal propagation through the grid, because we train different cells with subsets of data set. This is actually, as I told you, this was a starting point to do more or less something similar for federated learning. Imagine that you have in each island subsets of data set that you cannot exchange because medical data, for example. And we were able to see that with subsamples of data set, we were able to get better results. In this case, for example, with just 25% of the data, we were able to get more or less the same performance with than using 100% of the data. Well, and something really cool also is that we were able to see that when we increase the grid size, we are able to get smaller neural networks, that's for us something important, the same performance than bigger neural networks. So we were able to optimize better the parameters of smaller neural networks. And well, another excuse to show you Rita here is that we applied for semi-supervised learning. And something really cool I haven't said before is that it allows us to apply selection and replacement in our population. And one of the nice things here is that you can do this selection and replacement to keep individuals in your population according to some kind of criteria, not just the loss. So if you have like a specific, for example, we have used in I don't know, you know about physics-informed neural networks? So the idea here it was, okay, we are training using normal laws, regular laws, and so on, but we keep the ones that are able to keep better the physics of our neural networks. So it allows us to use other losses of fitness functions to use in our training. This is I say that because when you apply semi-supervised learning with GANs, you have another type of loss function. And the nice thing is here is that in each one of the cells, we optimize the networks according to different loss functions. And it allows us to get, again, good results. That's why they are here. We use the same, as I told you, you can select, for example, multi-objective optimization approaches to keep in your population the ones that are good according to criteria or more. we have addressed already or published cooperative coevolution, but for variational autoencoders. In variational autoencoders, you don't have this kind of adversarial loss. You have the reconstruction loss, for example, that they use together. So here we tested if this kind of spatial distribution of the networks could also be helpful in variational autoencoders. And of course, again, we get better results, blah, 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 blah. And something really interesting in this approach is that after that, as the nice thing of evolutionary computation is that we like to include more evolution things in our approaches. We included, it's not here in the graph, we included also pruning strategies to our network. So we were able to evolve at the same time pruning strategies to get smaller neural networks while we are training the neural networks. And the last thing is that we apply also cooperative coevolution in further learning. And the nice thing here is, again, it's not just we were training, we were evolving differential privacy strategies to not just to have like good reconstruction, also to get the privacy, to keep the privacy of our data. We are working in a project with banks in the US. They don't want to share the information. And well, the good news and the bad news here is that everything is open and you can just download and apply it, and it's really easy. The bad news is that I wanted to use Colab today to test that, but we just realized that Colab updated the Python version. So I need a master student to help us to update the requirements of the code. But as I told you, I have tiny versions and simple versions of the code of the approaches that I presented here in the collabs that you have or in the GitHub that I shared with you at the beginning, where I shared somehow. And I think that, I don't know if that's it.
They needed the cue, you know, to now.
Sure.
All right, question from my friend Jamal. Go for it.
Thank you, Jamal, for the presentation. I have a question regarding the use of LGD as a mutation mechanism. The way I see mutation is a way to introduce stochasticity to improve diversity, and LGD is kind of an informed mechanism and driven by the laws. So I was wondering if that could impact on the problem of a population collapsing, or if you tried other mutation mechanism.
Well, actually that was the main criticism to our approach, because it's not a real mutation, as we know mutation in evolutionary computation, because as you said, we should apply approaches that add diversity and stochasticity to our approach. Well, something that we did to address this, it was here, where instead of using one loss, each time we wanted to apply, to update the weights, randomly we throw a coin and we apply a different mutation. Well, that was let's say, the most stochastic way to do it. But that's right, so that's one of the more, so some people say that it's not an evolutionary algorithm anymore, if you don't use like mutation properly.
But you see an improvement of using the SGP. Why do you particularly use the SGP instead of the mutation?
Well, great question. Because when we started, the idea was to see how the coevolution, the whole framework, could improve the regular GAN training. So we took a regular GAN training and we applied the framework to see it. But really, it's a good question, and maybe I should think about it. No, thank you, thank you.
Any other question? Oh, there you go. Okay.
Thank you for your talk. Is it better to use a various population instead of if you want to mix the information for the different chromosomes you are optimizing, just extend them and use just one unified large chromosome? I mean, I see the advance of parallelize the computation, the search in various chromosomes. But it's not just better extend one with all the features you want to optimize, and it's always share the information.
Great question. Actually, I just submitted a paper where we addressed different, actually, 35 data sets, and we co-evolved feature selection, feature engineering, plus hyperparameter of, it's not nothing to do with GANs, okay? It was like classifiers, hyperparameter of classifiers, and feature engineering. And we observed that in this case, co-evolving them in one population, it worked better. But the thing is that the issue there is that when you have this one chromosome, you have to, at the end of the day, you have to apply operators that variate this part and variate this part in different ways. So you cannot apply like a regular crossover, because maybe you can like, at the end of the day, you would need to repair the solution, the chromosomes. But it's great because, as I told you, we thought, okay, we are co-evolving, it's always better, let's go. Now another paper. And at some point, wait. And we observed that for some problems, we didn't have any difference of co-evolve. Actually, we had like a little bit of improvement when we co-evolved in just one chromosome. Thank you.
Thanks for the
Speak
talk.
a little bit louder so the microphone will pick it, please.
Thanks for the talk again, really like it. And I have a question about how much does the topology matter? Because at the end, it's like, you already mentioned, like we saw that with a toroidal topology in the coevolutionary space, it's okay, but somehow, as it can be randomized, you can use another topology, and just if you will solve something or try.
Yeah, sure. We did a paper. I didn't mention there, but one of the papers here is that we evaluate the signal propagation here, and it matters because at some point you have like in your subpopulation and your neighbors some kind of knowledge that you share. If you bring individuals like randomly and you put them in the same, let's say, cell, they can impact in a negative way because you lose what you are learning and actually what you are propagating to the others. The important thing is that we need a topology, but we show that the topology, it doesn't matter that much as the size of the neighborhood.
Oh, okay.
But random topology, so getting random people.
No,
so
not randomly. I mean, let's say hexagonal instead of.
No. The thing is that it's important to.
The knowledge of neighbors.
Yeah, somehow. So,
okay.
but so the idea. So it's nice because several research that we have here it was because we had needs. We don't have enough computational power because we tried with the rings. So we have 1D topology. And we saw that with 1D topology, the neighborhood could be like 3, or keeping like 4 neighbors. And we observed that the size of the neighbor is what it matters more than the topology itself. Yeah. Great question.
Thank you.
Thank you for the talk. I'm curious to know when you apply the framework, the variation atom product, in which ways do you alter the loss function if you do so? Because in some part of the application to GANs, talk about some variation of the loss function. I wanted to know if you do also in the application of the framework.
I'm sorry, I'm not hearing you. I'm more or less deaf because.
In the application of the framework to the very general control.
Yeah.
Do you also alter the loss function?
We haven't tried that. Because like this is like something that we started like last year, and we have not enough students.
Can you maybe repeat what he asked for the microphone?
Right.
No, but with your microphone is perfectly fine. Just simply repeat, so people understand.
Well, yeah, thank you, Zach. Thank you. Well, he asked me about if we have used any type of strategy for the loss functions, like we did here in the other slide. No, in this work we haven't started yet to do any kind of. Not really, because now we are focusing more on this kind of federal learning approach with data privacy, with differential privacy. But as I told you, we need more students. So it's.
Does he have any idea?
Yes. No, but it would be nice. I mean. Thank you.
Great. Cool. Yeah.
Two little questions.
Please.
Have you compared, because at the end you're interested in generative networks, right? Have you compared the results with diffusion models, or have you, in your work, tried to use coevolutionary algorithms in diffusion models? Does it make any sense?
Being honest, is in our pile of things to do. But, well, so the thing is that we observed this idea, and actually we are, so as I told you, we need more students, people, or I don't know. Or maybe I need less administrative stuff to do. But yeah, because yeah, in Spain and so on, in Spain, you know to spend your time as a researcher doing administrative stuff. So the thing is that the idea here is that what we saw in this slide is that if you are able to represent the parameters of your whole model in separate subparameters, like in the GANs you have like the parameters of generator and discriminator could be like together somehow. We believe that always you can gain something, because at the end of the day you are trying to avoid, because at the SGD it's nice, it works, but it could stack in local optima. When we apply these approaches, the idea is that we're able to move in a way through the parameters space in a smoother way, and that's why if we are able to apply this to the diffusion models, we believe, and we want to believe we want to believe that it would work pretty well, but we haven't done it yet. And I want to tell you that.
That you know? Has anybody?
No, I have not. With diffusion models, no. So with variational quantum coders, we will see other approaches, also to apply evolution computation or coevolution approaches, but not with diffusion models. I haven't seen.
You need to hurry up. You need to hurry up before somebody comes.
You have to talk with my wife, you know.
All right. Any other question in the room? There you go.
One small question. I'm really curious about the time required to train all these generative models using genetic algorithms, and how much computational resources you need to do so.
Should we ask again for the
repeat?
No.
Yes, I know. So he's asking me about computational resources, time and a lot. Well, the bad news and the good news is that, so the bad news is that it requires maybe a bit longer, because you apply SGD and update the weights, which it takes the same time than in regular training, but you have to do all this part of evaluating the networks, applying, blah, blah, blah. But that's the bad news. The good news is that we trained the models in these different approaches using the same time, and our approach was able to get better results. In terms of memory, of course we need more, because we have a population of neural networks in our GPU. But the good news here is that we we're able to see that we're able to get smaller neural networks in inference time to get the same results than bigger neural networks. So, okay, we care about computational recursions. If we care about computational resources, memory, through the training process, of course, ours is more expensive. But if you think about inference, our approach is getting better results. Iván, ¿cuál es la mía?
Yo no he cogido ninguna, así que...
Changing of the topic of the question, I'm curious about if you try to analyze the resulting architectures of the discriminator and the generator, and so if you have any findings on or tendencies of the architectures. For example, in some slides before, you said that the discriminator is a very important part because it plays a key role in the training process, and you have to regularize it. And so I wonder if there is another finding, rules, tendencies in the architectures that arise from these genetic algorithms.
So the long story short, no, because in our approach we don't evolve the architectures. We are just training. So we're not doing NAS. This is also important to know. Yeah, actually, it's a normal question in these talks. So I was waiting for it. So long story short is that we haven't. As I told you, our friends from Coimbra, they are evolving the architecture, so you can check the papers and see. I don't remember. The thing is that it's really sad because I don't remember the results now, but I cannot tell you. And for sure, also long story short, it really depends on the problem. It really depends on the problem. Actually, in the source code I share with you guys, I've given you 3 different architectures to test. So you have like the one that is working and different architectures that leads you to mode collapse, vanishing gradient, and the oscillation. So you will see there if you want to see like.
Even when you say that you're working with small GANs, we are still speaking about a few millions of parameters, right?
Yeah. Well,
if that is the case, what is the population size that you're using to effectively explore the search space for that dimensional problem?
Great question, and maybe I have some results here. So here you can see the neural networks. So we have like 1.8 million parameters, 3.1, 6.1 millions, and we were able to, for example, this case, we have neural network with 3.1 million, like it's the half of this one, and we were able with 6 times 6 and 12 times 12, so 144 neural networks, we were able to train them, and we were able to get better results than the bigger ones, than the bigger ones. Well, this is a tricky result because we were able to run our experiments here. It was in let me remember the name. I don't know. Well, we were able to run it in Summit, which is maybe one of the biggest HPCs in the US. So that's why it's tricky. But we were able to, so for us the important thing in this result, it was to see that even with like huge population, like 144 cells on neural networks, we didn't diverge because we were expecting that we could diverge because it was like too big. But at the end of the day, there were enough communication through the cells to converge. Yeah. Thank you. Great question.
All right. Looks like we are coming to an end. Before you all run away, please bear with me. big clap, and you stop there, okay? Thank you very much. All right, before you go, a couple of things I need from you. First one is, as you probably know, tomorrow we're not gonna go to ski, all right? So the weather is not looking great. But we're gonna go on a tour in Granada City Center, right? So we arranged that, but we need to know how many of you are coming. Tomorrow it's gonna be raining possibly in the morning. So we are thinking about going at 11 a.m. We should be able to skip the rain, but you will need an umbrella just in case. And then we'll figure it out where to go after that, maybe going for some tapas or something, right? But the tour, we want to be able to provide it for free to you. But you need to let me know who is coming. So can you maybe roughly raise your hand and Ivan will be counting?
It's up for the.
Pero ya da igual, ya da
You
igual.
will count, right? Yeah,
Raise your
Pay
hand.
attention, guys.
Please, raise your hand in case you want to go to the tour. So guys, if you say you're coming, you're coming.
It's all recorded now, so your hands are up.
Perdón.
So we'll let please Carolina and Marta know before we go today. One more final thing before we go for lunch. I need your help. I need you to tie up your hair. We're gonna have to take a picture and we're gonna try to go outside. It's not raining at the moment, so we're gonna pretend that it never rained here in this school. And we're gonna go out, take a nice picture, and then go for lunch. Okay?
Nice picture with us.
Thank you very much. We're gonna try, I said, right? like a rock star, right? Like, hey guys.
Está en 5 minutes. We're waiting for everybody to arrive.
Shall we make a start, guys? Right. Okie dokie. All right, very good afternoon, everyone. It is my great pleasure to come back to the school with our next speaker, Steffen Schneider. I've been practicing my German, that is terrible. He is a tenure track group leader at Helmholtz, you made it very difficult, Munich, and an associated faculty member at LMU and the Munich Center for Machine Learning. And according to Google Gemini, maybe it hallucinated, this guy completed his PhD within the prestigious Ellis program, is that right? At EPFL, whatever that is. And then the challenge for me is to pronounce the next AI center that is something called Tübingen. Did I do it all right? Okay. You're picky, huh? Okay, you're really picky. But previously, he served as an AI resident at Meta, and where he worked a lot on self-supervised learning for speech recognition. Is that right? That's right. Wow, Google Gemini is fascinating. So I'd say I'm not going to continue reading this, but he apparently has a non-profit organization staff for school and AI and many other things. I think he's a great researcher when we talk about self-supervised learning especially, and I'm really looking forward to his talk, and I hope you join me already giving him a clap so he gets a little bit enthusiastic about it. The floor is yours, Steffen.
Yeah, thanks a lot for the super kind intro. So I want to talk about statistics in the age of AI. And talk about how we can use modern machine learning technology to really aid scientific discovery. If we think about the scientific discovery process, and I try to connect this a bit to the theme of the school, we have, so we basically have if we think about the scientific discovery process, we can think of a lot of different stages, from data collection, data processing, data analysis, to the information of new interventions that we can experimentally test. And over the past years or decades, the technology in data collection, that's mostly hardware and technology for sort of imaging in biology, neuroscience, biomedicine, so that really improved, but also our capabilities for processing data sets. We now have foundation models for a lot of different tasks and disciplines. Very challenging computer vision problems like object detection, segmentations are, at least on the benchmark, mostly solved. So these models are really powerful and useful to tackle a lot of these data processing needs that we have in science. And this really feeds into a lot of different disciplines. So neuroscience, we can record increasingly large scale data sets. This plot here, pay attention to the log axis, basically shows that the number of neurons in different model organisms that we can record is really scaling, is really growing exponentially and over the past years and still is. And we are at the point that we can basically do whole brain recordings at a single cell resolution in smaller model organisms in neuroscience. Then also in biomedicine, it becomes increasingly popular to do digital pathology workflows, digitize clinical pipelines, and there are now a lot of large-scale, high-quality, curated data sets that allow us to peek into sort of these areas and support also clinical decision-making with AI systems. And I would argue that our capabilities for collection and also processing outpaced a bit our capabilities to now actually take the data that comes out of this pipeline and draw insights from it, right? And this is the area where we move into the field of statistics, statistical modeling, data science, and this is what I want to focus about in the talk. So how can we use modern learning principles to build new algorithms that help us analyze these large-scale data sets and get scientific insights out of them? In my group, we studied this from different perspectives. So we are a machine learning group, but we have a lot of experimental collaborations. And in neuroscience in particular, you can study a lot of different systems. You can start at the human, of course. The human brain is ultimately often the goal, but then there are different model organisms that we study. We can look at the mouse, zebrafish, cell cultures, and organoids. And all of these systems come with different trade-offs because we can't arbitrarily record every single neurons in larger organisms. And as we, in the smaller model organisms, we have sort of more molecular and also electrical access to the system, but the system complexity is a bit lower. But interestingly, from the machine learning perspective, all of these model systems generate data that can be tackled with a common, or at least some problems can be tackled with a common set of methods. And I want to give you a glimpse into that. So the theoretical foundation for everything I will talk about today is this idea of identifiability. So when we want to use machine learning models that allow us to analyze data and draw insights out of them that we want to trust and then ultimately publish as a finding in our paper, we need some assurance that the representation or whatever formulation the ML algorithm gives us has actually some underlying meaning for the problem that we're studying. And for those of you with background in statistics, you might know this classical notion of identifiability. So when you have two statistical models, you put a likelihood function to these models. So this P, and then you look at two different parameterizations of the model that differ only in the parameters. You assume that okay, the pointer doesn't work that well. So you assume that these models match in their distributions, then identifiability means that this implies that the weights that you get are also the same. So think about some statistical model, you do maximum likelihood estimation, for example, you get to the point where the likelihoods match, then you can basically say whatever parameters these models estimate the mean of a Gaussian distribution, let's say, these would sort of match. So this is a notion of reproducibility, right? So if you apply the same technique multiple times to the same data set or to a resampled IID version of the same data set, then identifiability is basically this guarantee that the results and conclusions that you get out of your model won't change. So the caveat is now when we use identifiability with deep learning models, the same, if you think about a deep network, a lot of different weight configurations in the deep network will give you exactly the same model, right? You can do some scaling in one layer and then invert the scaling in another layer, and then the overall function that the model computes stays basically the same. This is why the field has come up with an adapted notion of identifiability over the past years. And here the idea is basically, so think about two deep networks, so it's this F, parameterized by a weight vector. So again, you can attach some likelihood function to that, cross entropy loss or whatever objective you're optimizing, or reconstruction loss in the VIE. And then again, you can say when these distributions match after training, then this implies that the two models match in their representation up to some indeterminacy G. And now the key idea behind a lot of the sections in the talk is to actually design learning algorithms and objectives to make this G as non-ambiguous as possible. So reduce it to a class of, for example, linear or affine transformations or even permutations. And that is quite useful because then you can basically take a very complex nonlinear problem, fit a model to this, and the ambiguity that remains is quite trivially to resolve. And the general pipeline is often that you basically say you have some kind of objective function, you can use this objective function to fit a model. Then from that you have this property of matching likelihoods, and then from there you conclude this match in the representation. Any questions about this? Because this will kind of be the basis for. Otherwise, I mean, in general, just interrupt me as questions come up. So now, so far we talked about the comparisons of two statistical models that we fit on a data set. We can extend this and introduce the notion of sort of the data generating mechanism that we assume behind our data set. So, I mean, we often in data analysis talk about latent variables, but the question is what do we actually mean by this term? So what is a latent variable in the context of an actual analysis problem? And one very useful framework for this is independent component analysis that has also been studied for multiple decades now. So the idea is you have some observable data, and we want to make sense of this observable data. The example I brought here is just a spike train recorded from the hippocampus of a rat. One possible assumption about the data generating process is that we say we don't necessarily care about the raw activations of all these neurons, we care about the underlying computation and mechanism that generated these data. You can formulate that by saying there are some hidden states, and these hidden states generate this observable data, and they generate them by means of some nonlinear mixing function, right? So there's some arbitrary nonlinear function, invertible typically is an assumption, that takes these hidden states, which are sort of low-dimensional hidden states, and then maps these to observable data. And this process we never see, right? So the goal now of scientific inference is really to infer these ground truth hidden states. So how do we do this? So we formulate a statistical model, and in this case, this will be a neural network model that takes the observable data back to a set of latents. And now the goal is to design algorithms where the reconstruction matches the internal hidden states as best as possible, right? So basically inverts this data generating process implicitly. And in this very general form, right, where you start with some low-dimensional variables, you map them using a nonlinear function, and then you just invert the whole process. This is impossible. So you need additional structure on the data. In the linear case, by the way, depending on how the samples in the internal states are distributed, this is possible, and this would give you classical ICA, right, which is an algorithm that is known for some time now. Okay, so the key idea now for this more challenging nonlinear case is if you introduce additional structure on the latent space, namely a lot of work out of Apo Hyvarin's lab introduced these notions of auxiliary variables. So you don't consider a pure IID independent distributions of the latents, but you assume that there is some regularity in the time series. So this is this variable u here. So let's say you co-record some auxiliary variable. The auxiliary variable could also be the time itself, which you can always record. It could also be the past time step. So it doesn't really matter. So and then from there are a few assumptions on the form that this conditional distribution has to take. But then from there, you can actually show theoretically and empirically that it suddenly becomes possible to invert this apparently quite challenging problem. And there are a few perspectives in terms of algorithms how to do this. And the two broad classes are contrastive learning, which is an encoder-only approach, right? You would train an encoder, and then in the latent space you optimize some objective. And the other approach are autoencoders for both some identifiability theory, what was already investigated almost a decade ago now, right? So this is a very well-studied problem by now. So I want to set the autoencoders apart for a second and focus mostly on contrastive learning. So if you look at some older papers, contrastive learning is really a learning technique that works across a lot of different modalities. So across text, speech, vision, then there are multimodal models if you think of CLIP. And it's a really powerful technique that also empirically performs really well and gives good representations. So a while back we wanted to study the problem, why that might be the case, and if sort of identifiability properties of these learning algorithms could be a source for that. So just a quick recap how contrastive learning works. So typically you have a setup where you have a reference sample, and then you have a positive sample, and then a few negative samples. Classically in computer vision, many approaches for the positive samples perform some kind of augmentation or slight variation in the image, keep the content the same, and for the negatives you would sample uniformly from the data set. And the goal is basically attract the positive sample embeddings in the representation and repulse the negative examples. And this is then basically the embedding space. So often it's also mapped to a hypersphere, how the embedding space then looks. So if you study a problem like this and make some additional assumptions about the underlying data distribution, then one assumption you can make is the following. So you can say that the reference samples for this anchor sample, this is uniformly picked from the hypersphere. And then you can also say that the latents from the positive sphere are somewhere close to the reference sample. So there's some concentrated distribution around the reference sample, and this is where the positive pair is coming from. And the negative pairs are again uniformly sampled from the sphere. And this data generating process between this hypersphere and the images is very complex, unknown, and we can't per se investigate it. And then interestingly, what you can show under these assumptions is that so if you minimize the influence loss, which is written here, which is maybe the most popular formulation that is used now in contrastive learning, then you can reconstruct a latent space that matches this unobservable latent space. In the case of the hypersphere, up to an orthogonal transform. So you get something like a rotated sphere, but you preserve the general structure. And you can actually show that this works also on a bit larger scale, still toyish data sets. So we, in this paper, we generated the synthetic data set 3D ident, and there are a few variants of this now out. So this is basically this teapot object, and then you can control different factors of variation. So the position, the rotation, or the colors. All of these latent variables you can imagine would be points on this hypersphere. And then our data generating process is Blender, and in the end you basically get an image, and then you can do controlled experiments. And the idea is now use contrastive learning, and for the positive pairs, use pairs that only have a slight variation in the factors. And then what you can do is you get a representation, you do a linear readout, as you typically do when you're evaluating representation learning algorithms. And then what you see is that if you measure the R-square between the ground truth latent factors, so the ones that generated the images and the ones that your model predicts, then this alignment is quite high. So 100% would be the theoretical maximum. And if you replace the computer vision pipeline with sort of a fully artificial process, you can get this even closer to the optimum. So this is really theoretical guarantee that also holds in practice. And interestingly, contrastive learning also has this property that even under sort of violations of some of these assumptions, you still get quite a good performance. So here's an alternative with purely synthetic data. In one case, the latent space is a box, and you have an unnormalized model. In the other case, it's a sphere. And what you see here is basically in orange the deviation from this assumption that everything is perfectly uniformly distributed. And you see that this R square of recovering the ground truth latents is quite robust to this. So now the question is, can we leverage these learning principles to actually perform scientific data analysis? And here's the data set again that you saw on the slide before. This is a data set out of the Bujaki lab. So initially, the goal here was to study the activation patterns of neurons in the hippocampus of a rat. While this rat moves up and down a linear track, you see the behavior and the neural recordings. And the neural recordings, like images, are high-dimensional signals. And the goal now, when we perform contrastive learning on these kind of data sets, is to go from the neural recordings and find embedding spaces that give us a faithful, low-dimensional embedding that captures something about the ground truth process behind these recordings. And typically, these scientific data sets are very multimodal. So here we have neural recordings and behavior. So you might want to do this on both disciplines. But you also, and maybe most interestingly, want to combine different modalities and sort of bridge information from these different modalities and answer questions how the neural data relates to the behavior that you are recording in your experiment. And if you look at these embedding spaces, so I mean, this is maybe more descriptive. So the color here denotes the position of the rat. You see that in the embedding space, the position is somewhat represented. But it's still, if you imagine this being a data matrix in your Jupyter notebook, it's still a quite complex data set. So you have 10,000 points with maybe 3 dimensions here. And dynamical systems offer an additional layer of abstraction to basically compress and compress the information in this further and give you a more compact description of the system, which is something that we will talk about later. One thing that I will skip over a bit is, so in the end, we're also interested in then mapping back these latent features back to the neural recording. So you may be interested in which neurons are mostly involved in these circular dynamics. And this is an information that you could then use in a subsequent experiment. So actually in the experiment setup, for example, stimulate some neurons and then observe how that changes the behavior. Okay, so to facilitate this kind of neuroscientific data analysis, when I was at EPFL in Mackenzie Martis' lab, we worked on an algorithm called Zebra. And the idea is here to use contrastive learning to essentially get these different kind of views on a data set. So you start off with these multimodal time series, neural data, time, behavior labels. And then you take the neural data, which is what you want to analyze, map it through a nonlinear network. Then you end up in the embedding space. And in the embedding space, the idea is now that you pick the positive samples according to the hypothesis you might have about the data set. So if you first of all want to explore the data set, you might want to ask, okay, I use time as the supervision signal, and whenever 2 points are close in time in the original data space, this should be close in the embedding space. You could also ask, if you think about this red, whenever the red is at the same position, is it actually possible to find a mapping that maps the neural activity to a similar point in the embedding space to get a representation of space? So this inference-E formulation is basically flexible enough to allow all of these different configurations. And then in the end, you get an embedding space like this. To step you through the process, here's some synthetic data. So you have a behavior label. So this is a scalar variable. So this is now the 2D embedding space. This is color-coded. And so I mean, you see there's some noise added. And now we step through this data generating process. So each point here would be mapped to a vector of synthetic neural activity. And then you apply this framework by pushing this neural activity together with the behavior label through this contrastive learning pipeline. And then what you get is, even though you never actually observe the latent space, you get a reconstruction of this latent space that matches the original one up to an affine transform. So this is post hoc aligned. And we can measure the discrepancy between these two embedding spaces by fitting this linear regression model and then computing an R-square. And with Zebra as a contrastive learning method, you are able to invert this problem quite well with very little variance, which is important because you never see the ground truth latence in a real analysis problem. So to maybe pause here and summarize sort of these first two sections, the workhorse of this is the fact that if you start from the inference-E objective, which is written down above again, you can you basically get this property of identifiability. And I wanted to maybe very briefly sketch how this works in general, right? So in the upper left, again, you have the setup where you have latent variables, you map to observables, and then from the observables to the reconstruction. The G is this mixing function that is fixed but unknown. The H is your neural network. This is learnable, and this is something is a quantity that you know. And for notational convenience, we often sort of just consider the full mapping from the latent to the reconstructed space, which is called F here. And then what you need to define as well is between the positive and negative samples some notion of similarity. So this is this phi here, or shorthand the psi. So this could be something like a dot product after you normed the embedding spaces, or it could be a negative Euclidean distance, or something else. And now over the years, there are different approaches to now go from minimizing of this loss function to the property that the reconstructed latent space that you get out matches the original one up to an affine transform or an even stronger indeterminacy. And I wanted to step through the second approach very briefly. So the key idea is that you basically say, okay, we have this inference-E loss, and we minimize this inference-E loss. So typically you consider this in the limit of having infinite many samples. So then the expectation that you would typically have in this loss function converges to an integral. You get a functional, and then you can study that at the minimizer of this inference-E objective. So there's a unique minimizer of this objective in the space of the similarity functions psi. And this minimizer, interestingly, is just a log density ratio of the positive and the negative distribution. And that's now really the key idea. So depending on your assumptions about how your data is distributed in latent space, you can now design a loss function that helps you invert this data generating process and infer the ground truth latents. So to make an example, what you would typically do is, after this first step, you would rewrite this in terms of the ground truth latent space. So we plug in the X everywhere. And then you have this function on the left. So this is basically the model. And on the right, you have your data generating distribution. And if you now plug in all the distributions, then you get a formulation like this. Because what you effectively did is you have some assumption about the P. Let's say it's a Gaussian distribution, right? So in the latent space, the positive pairs are roughly distributed like a Gaussian. Another good assumption for images would be something like a Laplace distribution. And then you design an inference loss that basically captures the log density of this assumption. And then you get this sort of formulation, plug this in, and this is looks like an isometry. And then from here, for different choices of the phi, could be a dot product, could be an L1 loss or an L2 loss, you can then basically derive the indeterminacy. And I noted down the special case here for Gaussian loss. So this is kind of the general idea or insight that with contrastive learning, it's relatively easy to engineer algorithms according to the particular assumptions that you have about your data set. An interesting side note is if you are skeptical about these assumptions about how the data is generated, there are alternative ways to formulate this in a weaker fashion. So you can basically skip the data generating process, and then there's some work again out of Abu Vivarin's lab and Geoffrey Röder and colleagues who studied this. So you can basically say if your model has a certain they call it canonical discriminative form, then you can also start from the neural data. And then from there just derive that two models that are trained with the same loss function and reach the same loss value again match up to linear transformation. And we discussed this a bit more in the paper and give additional conditions that are relevant for neural data analysis. So after this, let me show you how this actually now works when you have a real data set. So here's a real data set, observed data. And then from here we fit a model and then you get a latent space. So the question is now, so we have all these theoretical assurances that this algorithm makes sense and is identifiable under idealized conditions. But the question is, how do we check this now in practice? And for that, what you can very simply do is, on the same observed data set, you fit a bunch of models, make sure that they all converge and you don't have any optimization issues. Then you get these different latent spaces. Then you pick each of these models once as a reference example. And because of this indeterminacy, you know that these embedding spaces will all be the same up to an affine transform, right? They won't arbitrarily vary. So you can basically just fit a linear regression model or a CKA, CCA, right? Your favorite alignment method, basically. Align all of them and then quantify how well they are aligned. And in this matrix, you basically see the result of aligning all the embeddings to each possible reference example. And this is a measure of how well you are in terms of guaranteeing this identifiability also empirically. So it's like a goodness of fit. We call this consistency, not in the statistical sense. I should note in front of this audience. Basically in an idealized model, so if you would simulate data now that matches all the assumptions, you would expect that all of these scores are exactly at 100%. Okay, so if you apply this now to the red data set that I introduced before, we compared this across different models, and this is now a comparison that is not across different runs of the model, but is actually across different replications of the same experiment. So this experiment was essentially done with 4 different rats. And I mean, of course, there's some kind of distribution shift between these data sets. But for the sake of the study, the 4 rats were basically assumed to be IID samples for the question under investigation, right? So what you would expect now, if you train your embedding algorithm on all of these 4 rats, up to some differences in, that you cannot fully control for in the experiment, the conclusion you derive from them should more or less match up. And this is what we checked against a range of other methods. So here are some methods that actually use supervised auxiliary variables, and here are other unsupervised methods, T-SNE and UMAP also, for example. And what you note is that these contrastive learning techniques really outperform other approaches that don't necessarily have these identifiability guarantees in ensuring that you sort of get agreement and alignment between the embedding spaces. And again, I mean, the gap that you see now between the numbers and the 100% are now due to violations in the data assumptions, right? So this is not a data set with infinitely many samples, it's 10,000 samples. The mixing function is not perfectly injective. It would be if we recorded the whole brain, probably, but not if we only record 100 or 50 neurons. So this is sort of a measure how well you get to the achievable optimum. So if we now plug all of this together, this is how sort of a full summary analysis could look. So you have the neural data, you can visualize this latent space, and then you can also check that the embedding space actually captures something useful about the task. So it's a bit like the linear or KNN probing that we would do in representation learning models. So you could sort of, on a holdout trial, map the neural activity into this embedding space and then decode the position of this animal. You can also use much more complex signals as the auxiliary variables. So this is another data set that was recorded at the Allen Institute 5 years ago. So this is a video data set, and the mouse is watching these movie sequences. It's a relatively short video. It's 30 seconds and then repeated 10 times, 900 frames. And sorry, I think the animation stopped here. And so while different mice are watching these videos, you can record neural activity using different techniques. You can again estimate an embedding space, and then on a holdout trial, you can basically do a frame-by-frame prediction. What is the most likely of the 900 possible frames that the mouse is watching at each given point in time? And you can see that up to this intrinsic jitter, this kind of decoding task from the embedding space works quite well. This also extends this idea that you want algorithms that basically give you the same result if the underlying data generating process is the same. So in this experiment or in this data set, what's quite nice is that the same experiment was performed with two completely different recording techniques. So one neuropixels, that's basically an electrode that you implant into the brain. And the other one is an optical technique, calcium imaging, where you implant a window and then essentially take a video of neurons that become fluorescent when they're active. So two very different techniques, but the task is exactly the same. And interestingly, what you can show is that if you train this contrastive learning model on either of the two domains and then compute the agreement, again by the consistency, I mean, you don't get a perfect agreement, of course, but the consistency for this is quite high. And it's also a way to determine sort of the optimal dimensionality of the embedding space. All right. Any questions so far?
A small one. Why consistency is not a symmetrical score?
That's a choice. So I mean, you could use. I mean, if you use CCA or something like this, right, then you would align everything to sort of a joint reference space, then you get a single score. That is equally fine. The slight advantage of the asymmetric score is actually, especially if you develop new models, so you could have the situation that in one direction you drop a latent variable, so you have a 5D space, and you have some kind of collapse, and only 4 dimensions end up in the final embedding space. Then in one direction, you would notice, I mean, in sort of the forward direction, you would still get a perfect R square, but in the backward direction, you don't. So that's sometimes useful for debugging. Like during model development, we typically measure it in both ways. Yeah.
In this time-dependent data, how do you define the positive sample? So that you can respect the time consistency, and as we can see, there's like a trajectory in the manifold when you go around the manifold. How do you achieve that?
Yeah. So I mean, you could either specify a time delay, 10 samples, 100 samples, and then train with a fixed time delay. That's a hyperparameter. a hyperparameter that has a sort of a scientific meaning, right? That's kind of the time scale at which you model variations in the data. Or, I mean, the two examples that I showed here, so this is actually with the behavior auxiliary variable. So here you would take the position of the rat, and whenever the rat is in the similar position, that would define a positive pair. So it's a form of supervised contrastive learning, basically. And then here it would be so we take the video frames, map them through a dyno model, and then compute a similarity in the embedding space of the dyno model, and whenever that is closed, that defines a positive pair. Yeah. Further questions? Yeah.
Yeah, a question about the consistency metric. Is sufficient condition to guarantee that the latent space is good enough, or is it just something you have to do but you need something else? I'm asking about the collapsing of the information.
Yeah, you're exactly right. So it's the second thing you mentioned. So it's I mean the canonical example is you just map everything to 0, then you have a perfect consistency. Yes, so you need a mechanism to check that as well. Decoding would be one option to get there. I mean in practice, these fully collapsed solutions don't happen, right? So if you have a nonsensical fit, or something really goes wrong in the model, and you execute the training multiple times, you won't consistently get the same kind of collapse, right? So typically you would have some random embedding that is spread around in space, and it would look completely different between runs. So I would say, practically speaking, it's still a very good sort of single metric, but in general you're exactly right? Like the tuning would more be, you do it as a quality gate, and then sort of discard all the models that are below a threshold that you pick, and then from there you continue your analysis. Yeah. Other question? Yeah? Or maybe not. Okay. All right. Okay, so this part was mainly about using different kinds of auxiliary variables, so behavior variables, sensory variables you could see in the images, also time information to sort of get these different views on a data set and investigate a data set. I would now like to switch to the next algorithm. So here the goal was to learn equivariant representations and representations of groups. So if you think about a very different form of data set. So now we don't have a time series or co-recorded auxiliary variables, but we basically have data pairs. So this could be images, a bunch of images. We don't know the contents of these images. And between these pairs of images, there's some kind of transformation. So in this example, it's a rotation. And the learning signal that we have is we have a lot of these pairs. All of these pairs have contents. We don't know the content. The only information we have is that the transformation between all of these pairs is the same. So an example from biology is when you do experiments, you typically perform some kind of perturbation, pharmacological, for example, right? You want to test some drug. You have a lot of cells, you perturb them, and you measure them before and after you did the perturbation. The contents are completely different, but you want a representation of the effect. Another example is, let's say you work on robotics, and you have a robot arm moving. So then you would have some sensory information from the arm. And maybe you also record video data, right? So then you would have a lot of samples where, like in the real world space, you perform some kind of action, and you get paired samples both from the sensors that you installed and the visual information. And again, the question is, can you map this somehow in a space where all of these transformations that you do actually correspond to something meaningful. And from here on, it's a bit tricky with the terminology, because the word representation now means the actual representation in the mathematical sense of a group. So these transformations you can basically denote by this element G of a group. In this case, would be discrete or continuous rotations. And the underlying assumption about the data generating process is that you have this representation that basically maps each of these elements to an invertible matrix. And in other words, for each of these samples, you can find a point in an embedding space, and all of the points are transformed according to the same linear transformation. So that's kind of the idea, right? to sort of discover this latent space plus the representation of the group that denotes each of these transformations by some linear operation. The general framework is exactly very similar, so we come up with some encoder network that then maps this to latent space, and the question is now how to ensure that we actually get a correct representation of the group. And this algorithm that I will talk about can do this, again up to some kind of linear ambiguity and give you an equivariant representation. So here's the detail of the algorithm. So what you need to provide is basically a data set where you have two stacks of samples. The contents of the samples is arbitrary, essentially, but the information is that these two stacks of samples underwent the same transformation under some group, and you have a lot of these stacks, of course, right? You don't just have a single example. You have a lot of these and a lot of different, let's say, translation by different offsets, rotation, and so forth. And now what you can do is you can map all of these samples again to latent space. This is denoted by the X here. You take one of the samples out, and the other samples remain here in this middle part. And from these samples, you estimate the optimal linear predictor that goes from one batch to the other batch. So you essentially just compute a linear regression. And this is your, we call this implicit representation of the group element. Implicit because this matrix never really exists anywhere in the model. It's not a set of learnable parameters, but it's sort of implicitly given by having the examples and then fitting a linear regression model on the fly. And then what you can do is you take your reference example in the contrastive learning and you map your reference example with this inferred matrix to the next sample. So what you're essentially doing is you tell the model, I'm interested in this kind of transformation. I have a bunch of samples here. All of these samples underwent this transformation. Now for this new sample, tell me how would that look if I transformed it in the same way. That's kind of the intuitive idea behind this loss function. If you look at this, the likelihood here is again this familiar part of the info NCE. The addition is that here you have this linear predictor, and you learn this algorithm sort of fully end to end. So again, under some assumptions, you can give identifiability guarantees. In this case, so here's a depiction of the setup again. You have the latent space with this linear matrix. You have the observable space, and then you have the model that maps this to reconstructed space and then finds the transformation there. Under assumptions, again, I mean, the mixing function has to be injective. There needs to be some diversity in the samples and the data set. You get as results that the latent space is identifiable up to a linear transform. So you will again map all of these images to a useful vector representation that matches the ground truth one up to a linear transform. The group representation as a consequence is also identifiable. So basically recover all of these matrices in a way that they are applicable in this linear transformed space. And you get this equivariance property. So again, this H denotes the full mapping from the original latents to the reconstructed latents. And the equivariance property basically just means is that if you look at the representation of a transformed sample, or you look at the representation of the sample and then transform it, that gives you the same point in the embedding space. So you can verify this now on synthetic data. So what we did here is change the difficulty of the problem, so make the mapping function more nonlinear. What you see is that EDC is able to handle this up to some point where the problem becomes too difficult. To detect this, consistency is again the right metric. To tackle it, you can simply record more data, then the drop would come a bit later. Another variation is the kind of group we are studying. So this is now all synthetic data. So we can very easily sample matrices with different properties that we apply in the latent space. So for an orthogonal group, the estimation works pretty well for dimensionalities up to 9D, maybe even more. For the general linear group, you get a decay at some point. So there turned out to be important that you actually also backprop through this linear regression scheme. And now here's on a, still toy data set, but more computer vision a toy data set where you can actually imagine these different shapes. You see between the shapes there was some kind of action applied. So on this kind of data set, it's very easy to generate. I mean, it's a form of D-sprites basically. And on this infinite D-sprite data set, we trained the model. Intuitively, what do we expect? So the transformations that we have here is a translation in the x direction, in the y direction, and then a rotation of the samples. So these are basically the actions that we considered. And when you train EBC, this is how the embedding space actually looks, right? So so this is sort of a collection of, I mean, if you sort of generate these trajectories of moving shapes and then construct the embedding space for these shapes, you get this toroidal topology. The x translation is mapped across one circular coordinate and a y translation along another one. And maybe important to note, so besides the fact that we give these paired examples, this is a fully unsupervised or fully unsupervised kind of technique to, so there's no prior that would tell the model that this is the right embedding space. One way to quantify this, so there's a bit of a shortcoming of contrastive methods where you only have an encoder. You can't verify the representation by just generating a few samples and visualizing them. So instead we do the same that we did for Zebra. We do a KNN lookup and basically give a reference example and a perturbed example, compute the optimal transformations, and then look in the data set where we actually end up in the data set and what the most likely sample is that the model would return, which works quite well. Again, this is a useful algorithm when it comes to scientific data analysis. It's basically a variant of this behavior contrastive learning that we discussed before. With the difference that now we no longer say whenever the red is at a particular position, this should map to the same part in the embedding space. Here we would now say whenever the same action is performed in the experiment, this action should have the same representation. So that means whenever the red is moving 10 centimeters or is changing the direction, which never happens in the data set, so this is something that comes out of the model, this should be represented consistently in the embedding space. And if you look at one example here, so you basically see these movements, you get essentially a vector field out of the algorithm. And the switch from here to here is basically a direction change while the position stays constant. And you nicely see that the embeddings are sort of quite nicely aligned, and you can kind of, in the embedding space, simulate what would happen if I would flip the red now in place. And this is something that you see across all of these different data sets. All right, any questions about this part? So then, we will modify the assumptions even further. So now we're back to dynamic systems analysis. So here, what you can say is, suppose you have some time series data, then a very useful structure to impose in the latent space is that you say you have some kind of latent dynamic system that generates your data. So you can say your hidden states are not just evolving according to some probability distribution. You can give this distribution a bit more shape and say there's some kind of transition function plus a noise vector. This transition function has to be bijective for what we considered here. And the question is now, can you recover this latent space, but also the transition function that governs the dynamics? And this would be quite useful because then you actually have a very compact description of how the system works. You could, if you think about world models, right? That's essentially one of these ideas that you have a lot of observable data and you model a transition function that is actually useful to sort of predict ahead in the future. Maybe do model predictive control and steer system towards a certain state. And the question is, can we do this with identifiability guarantees? The answer is that we can. So the algorithm Rodrigo and Tobias came up with basically again takes a time series data set like this, reference sample, maps the sample into the embedding space, does this for the positive sample as well. And now the crucial addition is that we have this dynamic system, so that's some parameterized function what we select is the class of function. So that could be, in the paper we considered just linear dynamical systems or switching linear dynamical systems. In theory, you could also plug in an MLP or a neural ODE. At least there's nothing like fundamental. Contrast that against all the negative pairs in the embedding space, and then what you get out is sort of a reconstruction of the latent dynamics along with an explicit readout of what this transition function actually is. So to step you through the process, so here's some simulated data again. So this is a slightly more complex system than just purely linear dynamics. So you have this latent variable Z. So that's just that's basically just a discrete variable. And each of these colors then match one of these linear matrices that you see on the left. And then the system evolves according to the switching linear system. So whenever the state has the same color, you would pick the same matrix for evolution, and then you have the switching point and then switch to a different mode. So this is now mapped to the observed data space. And Tobias came up with an elegant formulation of the switching linear dynamics that don't need any Bayesian estimation of the state. So this is just differentiable. You can plug this into the training objective and then on the fly estimate different switching matrices. And then in the recovered latent space, what you get are again several indeterminacies. So you get so the original like this state that switches over time. There you would have to resolve a permutation because these colors of course don't mean anything. For the space itself, you need an affine transformation, and then the matrix that you estimate as part of this affine transformation is also the ambiguity for the dynamical system. Here's a numerical comparison between this. So what's quite interesting is to contrast this against the time mode of Zebra that we considered before, because that was also able to estimate useful embedding spaces, even though it didn't have a dynamical system parameterized and fitted at the same time. And we think that the answer why both can be true at the same time is that so whether or not you need to fit these latent dynamics depends on the trade-off between the amount of noise that you have in the latent space and the effect of the dynamical system. So we simulated this here. When you have matrices in in the switching linear dynamics, where think of the matrices for simplification just as rotation matrices. If the rotation that each of these matrices does in the latent space is relatively small, and then you add a lot of noise to it, then you actually don't need to bother about the dynamical system. Then it's completely fine to just do time contrastive learning, and you will get quite a nice performance. If you now lower the noise level, so that's the switch from the solid lines to the dashed ones, then the standard time contrastive learning already drops. And then as you increase sort of the magnitude of the angles in the matrices, you see that this baseline without a dynamics model really drops, and while the dynamics contrastive learning performance stays close to the optimum. Here's the identifiability guarantee again. So you have this affine ambiguity for the representation, and this translates then. So you fit the parameters there, and then this translates to the transformation of the dynamics function, and you can again verify this. We also tested this for nonlinear dynamical systems, so a Lorentz attractor, and this surprisingly also works quite well, so without even parameterizing the right transition function. So what we did there is a switching linear dynamical system with something like 200 modes, and then what you essentially do is you piecewise approximate the linear system, so that seemed to work quite well as well. Here's an application of the method to this red data set again. What you can maybe appreciate as the difference to the time contrastive model. So this fitted with the linear dynamical model. So you really get this kind of ring topology, which makes sense because the task is very, very repetitive. And you can then post hoc, so this is unsupervised of course, so you can post hoc estimate a phase and then sort of study how the different neurons, the firing patterns of the neurons align with the phase, and this is exactly what you would also expect for this data set. So the primary publication essentially looked at play cells which selectively fire for particular locations in space. Another example on this Allen data set. So this is the embedding that you get here, which again, as you might appreciate, looks a bit more disentangled than the one we saw before. Again, this makes a lot of sense because here you have, as I mentioned before, 10 repeats of the same movie. And interestingly, if you fit this together with a dynamic system, these repeats actually really become visible. So this is colored by the frame time, and you have something like a loop closure property. Again, time is the only supervision signal, right? There's no underlying information about the task. And this is now quite interesting. So for the area this was recorded from, this kind of result makes sense. But you could imagine that you apply this now to a different brain area, and then you would expect that you get much more nonsensical dynamics out of that, and can then investigate this further. And at this point, I maybe want to comment a bit also on some of the questions that were already asked. So in practice, how do you actually fit these different kind of statistical models? So for this, we just released the library that we use to do this internally. So the idea is that this property of consistency that you can use whenever you have identifiable algorithms is really something you can use for hyperparameter optimization and AutoML when fitting these models. So consider a bunch of different models. DCL or Zebra, for example, you would fit them into this consistency ensemble. And only thing you need to know is, these models need to adhere to a scikit-learn API. And then what very simply happens is you train a bunch of these models and then specify the class of indeterminacies. And to align the representations or parameters of all the models, we then automatically determine this indeterminacy. And you could use that then for hyperparameter search and model validation. If you're working on data analysis, we literally just today released a library. We are really happy about some beta feedback. So it's on GitHub. And this is how it looks in terms of the code. So it's really just a simple wrapper around a scikit-learn model that you could otherwise use for data analysis. And so to briefly take you through this, you start from data, train a bunch of models, perform inference, you get a representation, then you align all of these representations with the class of indeterminacies that you have, and then you can do some kind of aggregation, maybe bootstrap some uncertainty estimates. Tobias did this here for this Allen data set. These are PCA projections of this dynamic system that you just saw. Post-hoc, you can again all align these. And then above you see the consistency between all the models. Here you really nicely see how you can use the consistency to make informed choices about the hyperparameters. So what is varied here, so the x-axis is a baseline without a dynamic system. The y-axis is the variant where you use a dynamic system in the fitting. You see the consistency for both of the models. This dashed line is basically the sweet spot where it doesn't matter whether you use the dynamic system or not. You see exactly this pattern that I mentioned before. So when you model on a relatively short time scale, where the dynamic system is maybe less important and the noise actually dominates, it doesn't really matter which model you use. And also in general, the consistency is not that good. So now along this axis, we increase the time offset. So basically the time delay for picking positive pairs. And what you see is that the consistency improves. It makes sense to model the dynamics explicitly. And you can also make choices about what the right dimensionality of the data is to fit on, for example. And then finally, when you have all these models, because they are all aligned, you can use them, in decoding, you can ensemble in the embedding space, get better decoding performance. There's an example in the Zebra paper for that, actually. You can also do it for estimating uncertainties. So you can compute a mean trajectory and then uncertainties. Because in these data sets, it's actually interesting. Is this a single line that is looping around, or are these actually different lines, and are there more fine-grained dynamics that are statistically meaningful? So this you can can very simply do just by running your model a couple of times. You can also notice sort of limitations in the fitting, right? So here's a study where we artificially reduce the number of neurons that the embeddings are fitted. And what you can see is that this gradually collapses to a very noisy form of the embedding, where the uncertainty estimates also become larger, the consistency drops. And this is most likely simply because when you have less neurons, then this injectivity assumption on the mixing function gets more and more violated. There's more and more ambiguity in the data set between sort of the ground truth latents you want to estimate and the actual data. So this works quite robustly, and is also a useful technique for tuning and working with algorithms that maybe don't yet have a perfect theoretical guarantee. So it's also for us a bit of a research tool. So if we develop a new algorithm, you can kind of guess an indeterminacy that would make sense, and then sort of start tuning models, and then gradually move this towards sort of a more rigorous treatment of the algorithm. So for the last 10 minutes or so, how am I doing on time, by the way? I think it's, yeah. So for the last part, I want to move a bit away from the neuroscience use cases and talk about a second very important model system that we can study, which are deep networks themselves. So why is this relevant? So as I said before, especially in, I mean, we're working a lot in this biomedicine domain, and there are a lot of really great use cases where the data sets are sufficient. You can train large scale machine learning models and potentially embed them into clinical use cases or other high stakes applications. And for these cases, it's really interesting and important to actually have a peek into these systems and understand what the basis for different decisions are. So forgive me this very oversimplified picture of what happens when you paste this picture into ChatGPT. The point I want to make with this, what we're interested in for the papers I will show after this, is to basically hook into any foundation model that you're interested in, and then make statements about sort of the concepts or motifs that these models use for processing a data set, and potentially also linking that again to the text, right? So really checking internally what are sort of the computation motifs the models are using. And a very popular approach for this that came up in the past years, and Anthropic does a lot of great work in this area, especially in language modeling, are sparse autoencoders. So in the sparse autoencoder, the idea is that you take tokens from your network vectors, and you map these vectors to very high dimensional space. So let's say your foundation model would start at 1,000 dimensions or something like that. Then in the embedding space of this SAE, you would maybe go to 40,000, 80,000 latents. And then you impose a sparsity prior and solve a reconstruction plus a sparsity objective simultaneously. And the goal is basically for each point in the image to get a very sparse and informative barcode. So it looks like this. So this is an input image, and this is now for a model that we presented last year at iClear. And what you can do with this, you can basically query a patch in the image of a clip model or some other vision model. You map this through the SAE, and then each token gets assigned, gets one of these barcodes assigned. You can aggregate these barcodes across the image, and then also perform lookups and represent the sort of feature that is important at this particular point in the image by the most representative images, along with an along with an attribution mask that is again computed with a barcode. So in general, right, like each of these patches has a barcode on its own, and you would highlight the ones that are active for the one that is highlighted for the query patch. And what's interesting about this approach is you can describe these concepts, I mean, even without tagging them with language. It's quite easy to read this. So if you query the patch on this grass in the background, these would be the maximally activating images. And when you look at the overlay, you actually get images from a lot of different ImageNet classes. But after the overlay, you see that the grass is actually the concept that is relevant. So you can make these sort of visual comparisons quite nicely with these SAEs. You can validate them in different ways, so different ways of quality checking that we also discuss. A very useful one is simple ablation. So you order the concepts by importance and then you ablate them and see the drop in downstream accuracy. And if you identified good concepts, then only very few concepts will be sufficient to cause a serious drop in the performance. There is also a lot of work on then automatically categorizing these concepts. We studied this in a paper last year. And so here the idea is basically that you have concepts that are relevant for the target classification. So these would be the ones, if you ablate them, the target accuracy basically drops. And then there are bias concepts in the data set that are not really important for determining that this is an image of a dog now, but are still recognized in the image. And then these kind of automated ways of categorizing are quite useful to perform investigation of data sets. So for example, in an almost completely unsupervised way, determine if you have unwanted biases in the data set and then potentially debias, resample some aspects of it using these sparse autoencoders as a backbone. There's also code up for this one. And finally, I want to get back to the domain application. So in medical imaging, we recently applied these sparse autoencoders to some foundation models for the single cell images. So in general, these are samples from so single cell samples from leukemia patients. And there's an automated digitalized pipeline and also a way to perform cell type classification of these individual images. This can be pooled across different data sources. And our collaborators 2 years ago published a sort of first computer vision model that sort of compresses all of these data sets and that we then use to train an SAE on to actually peek into the internals of these medical foundation models. What's interesting about these data sets is that they are often very hierarchical. So you, on the patient level, you have 500 of these single cell images per patient. Then you have the patient, and then from the patient you could aggregate and go to the level of diseases and then study what the differences are on that level. And in general, the intended result is here that in an unsupervised way, you classify different of these morphological concepts in the SAEs and then can use that to study certain questions about, that I will talk about in a second. So before I go there, important again, we use the same sort of mechanism of filtering pipeline inspired by the consistency that I talked about in the first part of the talk. Because you, like after training the models, you end up with 50,000 possible concepts, and a lot of them are not really useful. Maybe are not interpretable, they are not popping up if you retrain the model. So we do as much as possible automated quality control, because whatever comes out of the pipeline, this is something that we would validate with clinicians then. So you would really want some way of automatically filtering this. So the idea again is very simple. What you do is you don't train a single model, you train 3, 5 or 10 of these sparse SAE models. Then there are a few simple filtering steps. You filter out concepts that are never active, so there are some quality scores. Then you filter this down to around 2,500 concepts. And now a useful indeterminacy for this kind of problem is that you basically say the autoencoders should match up to a permutation. So you need to sort of align all of these models up to a permutation. And then after the permutation, you could define different metrics. So you could say we're interested in optimizing the cosine similarity between the decoder weights, because it's just a single decoder layer. Or what also works quite well is you actually directly think about how would you visualize this later. You would visualize this by showing example images of these different concepts and overlaying it with a mask. So another good criterion for doing this matching is that you basically say how many of the top 10 maximally activating images are overlapping. So you compute essentially an overlap score. So when you define the score, you can do this matching, and then at the end, you end up with maybe a rough, for this data set, roughly 1,000 of these concepts that you can then annotate, validate, and use for further analysis. So this is how this looks. This is I think, non-cherry-picked example of a few concepts. So here are the 3 different SAE models, the more consistent ones. What you can see is that the images more or less match, so the order can be different, and also the masks are more or less consistent. And you could again imagine an aggregation step where you compute an average. And then for the inconsistent ones, I think this here is the most extreme case. Here you have completely different images. So this is not a really useful concept, and this is something you would throw out in the filtering process. So now again, you can validate how useful are these concepts actually for tasks that are relevant in the context of this data set. We are now at the level of patients. So this is now a classification task where you predict the leukemia subtype. First of all, you categorize healthy versus patients with leukemia, and then within the leukemia there are 4 different subtypes that you can distinguish based on the morphology of these cells. And the red line here, that is a fully end-to-end multi-instance learning deep learning pipeline, right? Where you sort of go from the single cell images and then to multi-instance learning to predict the disease class. And the white line is essentially an L1 regression that you perform directly on the filtered concepts. And what you can appreciate is that at some point you reach the same performance. So in general, you don't lose that much information when you do this mapping onto concepts. But if you are willing to sacrifice a bit of performance, then with around 9 active concepts per class, you are able to almost get to the level of the baseline while being much more interpretable, because you basically just need to look at the 9 different at sort of 9 representative examples of the cells. And then here on the right, you see some aggregated examples. Some are named already by a medical expert, others not yet. And this can then again be used to sort of double check sort of what the model internally uses for classification. You can also aggregate this one step further. So a useful way to think about this is, so you know the class labels of the different disease subtypes, and you can now aggregate the barcodes up to the disease level. And because they are barcodes, you can essentially compute a diff. So you can take your data set, split your data set in 2 groups, and then compute a diff between the groups. And the diff that comes out would be concepts that you can analyze that are somehow distinguishable between these 2 classes. So I think an interesting case would be if you have a classification model, and the classification model on some task is very unintuitively much better than a human. You could use this to sort of investigate, are there any sort of visual features that we don't know yet, but that we could adopt that the model uses. Or you could use it to detect sort of shortcut solutions and something like this. Anyway, so if you compute this diff, you can again perform a statistical test on this. So basically check that this difference that you observe over the representative samples is above chance. And then here I visualize some of the disease-specific concepts that we got out of this. And with this, I also want to conclude. So the overall 2 messages I want to send is, first of all, contrastive learning I think is at a really interesting stage now. There's been a lot of theory work on it over the past years, and it's now possible for data analysis problems at hand to really design statistical procedures that match what you need to want to investigate for your particular data analysis problem. And I hope I could convince you of 3 examples of this. So Zebra for using different auxiliary variables. In this neuroscience case, then EBC for learning equivariant embeddings, and DCL for sort of inferring latent dynamical systems, where we also want to identify system description. And this really has wide applications, so we are working across a range of different different model systems with our collaborators and are applying these techniques also to real-world data sets. And then I think the second approach I'm really excited about are sparse autoencoders. So what is quite elegant about them is that the algorithm framework transfers really well across different foundation models. So as long as you have a well-trained foundation model, in the sense of the word, right? So really a model that is good at few-shot or zero-shot adaptation and generalize as well. You can plug these SAEs on top, and they are quite useful for understanding internally what's going on. I showed this in the showed patch SAE. For that, we also have checkpoints available, Cyto SAE for the medical examples, and we have a few examples on language models and neural data actually as well. Those of you who fit scikit models from time to time and are interested in the identifiability part, we just released this iTuner library to make this consistency tuning a bit more seamless. That's also what we use internally for data analysis. And yeah, in general, for Zebra, there are a lot of demos to play around with on the website. Okay, and with that, that's the end of the talk. I want to thank everybody in this. Everybody who participated in the work I showed. I showed some older papers that I still did when I was at the Tübingen AI Center with Matthias Bethke and at EPFL with Mackenzie Mattis during my PhD. And yeah, this is the last year snapshot of the lab with good weather around Munich. Most of the work from the lab I showed today was from Jesu, Tobias and Rodrigo, and Furkan, of course. And yeah, thanks for listening and happy to take some questions.
I'm super surprised he's got time to go hiking after all those papers.
Now and then.
Every now and again, yeah. Julian, please.
Yes, in your work about identifiability of groups, did you say that you need the group to be finite?
No.
No, okay, so you can deal with SO3 or SO2?
Yes,
okay.
Yeah, I mean the examples I showed, I mean, actually not right for the D-sprites, it is effectively a finite group, but there's no restriction in the algorithm. Yeah. Okay. What we didn't cover in the work is sort of, I mean, so for example, to get the generator or something out of this, right? That would be a post-hoc processing step. That is not, what you get is basically for all the examples in your data set, you get a matrix. And you could potentially apply some decomposition then on the matrices to analyze it further. Yeah.
Thank you very much. I really enjoyed your talk.
Thank you.
The question is, will this concept of using sparse autoencoders apply to data space of self-supervised models could be useful for building some kind of semantic space for zero-shot learning?
For what?
For zero-shot learning?
Zero-shot learning. I would bet that there's work on this. So yes, I think in general, do you have something in particular in mind? I mean, in general, what you get out is, I mean, especially if you train the SAEs on a multimodal model, right? So on the CLIP model, for example, you could do this for both the language and the vision part, and then even link the two modalities. So I mean, depending what the exact system is, I mean, yes, I would argue that it's probably useful in some way, but yeah.
I was thinking if I understood correctly,
yeah.
You talk only a few activation of this sparse autoencoder.
Yeah.
And you can interpret what's the visual features of that activation.
Yeah.
So you can describe a new class that it has not seen with these activations.
Yeah, I mean, I guess one implicit assumption with these autoencoders is that the foundation model has kind of seen the whole data distribution already, right? That there's not, but I think what is actually maybe one way to think about it, we actually studied this in the ICLIP paper. When you do adaptation, So, I mean, if you have the assumption that your foundation model was basically trained on the whole data distribution, it can still be useful for a downstream task to focus on a particular subset, right? And for that, the like this concept representation, I think is useful. I think I've seen a few papers recently, for example, using it for kind of classical covariate shift adaptation, where you need some kind of measure where in space your data is distributed. And I think for this, the semantic layer is interesting. Yeah.
But maybe the problem we've got in zero-shot learning could be that, you don't know there is that class.
Yeah.
So you split, let's say, whatever, a lion and tiger, and then you say, well, compared to the rest of the classes, they are relatively close.
Yeah.
But then all of a sudden something happens like a leopard, whatever, in the middle of
Yeah.
it. And then it becomes a little bit more challenging to detect. So somehow, I guess, the question would be, how could you make embeddings even more separable somehow, just in case there is something that makes sense in between classes?
It's more of a few-shot learning case, really, no?
No, it's zero-shot because you don't know until the very moment that the system is in deployment. So you're deployed, and then all of a sudden someone tells you, oh, by the way, there is something called a zebra, there is something called blah, 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 and then you need to be able to detect that with that description, right? What our friend Zhang was suggesting.
But I mean, you definitely need some machinery on top of this, right?
Yeah,
so I think one kind of adaptation technique that could be interesting is, I mean, in a vision model, that you basically enter something like a system prompt into the model, right? And I mean, this has been done with trainable tokens or something like this. But I mean, I think there the SAEs offer a possibility to sort of edit something that the model is doing while being able to interpret the semantics of it. So maybe something is there, but it's...
maybe the two of you need to get together. And at some point.
Happy to talk more, yeah.
Good, thank you. Natalia, please.
Yes, maybe you could elaborate a bit on the concept of disease barcode, because maybe I didn't understand really, like, do you have a vector of all possible concepts that can be indicators of a disease? Is that what it means?
Yeah, so I mean, in general,
could you maybe repeat a little bit what she said so people understand?
Okay, because of the so the question is if I can elaborate on the concept of a barcode in the concept of the diseases. So what is a disease barcode in this context? So it's so what the sparse autoencoder gives you is, I mean, what I mean by barcode is just the activation vector of the SAE, basically, right? And then optionally, you could apply some kind of thresholding and say, I mean, if you want a binarized representation, right, you could say that the activation is above some threshold and below you have a 0, above you have a 1. But that doesn't matter that much. So in general, by barcode, I just mean the SAE activations. So you have that on the level of each patch in the image. And then what empirically works quite well is that you simply aggregate this by computing the mean across sort of the hierarchy of your sample. So to get to the disease, you would aggregate the barcodes from the patch to the image level, then from the image to the patient level, and then from the patient level to all the patients that had this particular disease label. So it's really just averaging activations of the SAEs together. Does that answer the question?
I was thinking that maybe you could point that, okay, this disease has this concept, like this particular cell shape.
Yeah.
But you know, because you normally don't have these annotations by the medical doctors, right? So I was wondering how you name all these concepts without having to bother the doctor all the time. Like, do you in practice have these annotations, or to validate that they actually are meaningful concepts that you are?
So in practice, so the question was, is there sort of an unsupervised way to label the concepts, right? So I mean, I think for natural images, yes, right, you push them through GPT or your favorite model. So for the medical images, we intentionally don't do it. So it's really designed as a human in the loop system. So what we have is basically a web platform where all the concepts come in and then clinicians log in and actually do the labeling and verification. And then, I mean, the hope would be, so I mean, in some sense, this data is recorded anyways, right? It's just not fully digitalized in the workflows right now. So I think the idea would really be to build up a database where you, I mean, essentially what you do is you ground your foundation models in actual knowledge that you would get from an expert. And I mean, at least for the sake of this, I would argue that it's actually fine to have the expert in the loop for that. Because what you gain from this, so the more concepts you have labeled, you could then actually like propagate these labels to the automated diagnoses that you do potentially, right? So it's not, you don't fully automate the human out of the procedure, but you use the human feedback at this point where you get sort of a very compressed sense, okay, this is a concept that occurs always between these two diseases. So that's kind of the idea here. I mean, at the same time, of course, people are working on sort of automating the labeling step, but yeah.
First of all, thank you for the presentation. Actually, I'm doing a PhD in a very similar field, which is contrastive learning and neural activity. So, and your work with Zebra was kind of inspired me to do this part. So what I was thinking is like when we generate the latent space, it's tuned somehow to only one factor of complex data generated process. Like, for example, for the rat, it's tuned to the behavior, but maybe there are other factors which are affecting the rat to generate this pattern of the spike. Do you think we could somehow benefit from factorizing the data generation process into the small parts and generate multiple latent spaces, for example, which are all combined to represent more complex dynamics behind the activity? For example, what I'm talking a concrete example is I'm working with the example of neuroplasticity, and there is a behavior which is slowly changes between multiple sessions, and somehow it's very difficult to detect, to represent this part in the latent space. So maybe somehow contrastive learning can help us to generation of the combination of multiple latent spaces.
But so this separation into different parts, you still have different auxiliary variables for that, right?
Yeah.
So, or not?
There are some of them because there is the repeated process which is between the sessions, but there are changing patterns which may be related to neuroplasticity, and we somehow want to separate this pattern, but still we cannot come up with factor to affect, like for example, for the some factor to modulate this representation.
So there's one rather straightforward solution that I would say works surprisingly well for this. So what you can basically, I think I don't have a slide on that. So what you can basically do is you say, here is your embedding space, 100 dimensions, and then you just train multiple of these models at the same time, right? So you basically put, so what you could do, for example, is you train the whole embedding space on some with time information, for example, right? And then you just have, I don't know, the first 10 dimensions, the next 10, the next 10, the next 10, with different behavioral variables. For time, I think what could work is that you also, I mean, you could stack different time scales together, right? You could say one part is trained with on the second scale and the next on the 100 millisecond, 10 millisecond scale. So something, I think something like that is probably a good first start. And that works. There's actually in the software library, there's an API to do exactly this. So to basically engineer this kind of embedding space and attach different loss objectives to different parts.
And you have to like align the embedding space between each. For example, if you train the multiple models, as you showed before, no, like you align them so that each dimension of the representation space is responsible for the same.
I mean, the interesting thing that happens if you do this partial supervision is that the indeterminacy becomes stronger, right? So then you would get a block diagonal matrix instead of a linear transform, because of the. I mean, not because the model does something fundamentally different, simply because you put more knowledge into the into the system. Yeah. So yes, so this alignment step would work a bit differently then. So then you would probably train. Yeah, I mean, you would basically need to constrain the matrix to be block diagonal with useful sizes of the blocks.
Thank you very much.
Alberto, please. Thank you, Steffen, for your talk. It was very inspiring.
Of course.
You presented us here a way of a mathematical formal way of creating positive samples out of a network via a group, a permutation or rotating group. And I wanted to ask you if you have considered using also a mathematical formulation for creating the negative samples?
In this work, we don't. We talk a bit about it in the Zebra paper. So, so it's a useful way to build invariances in the model, for example, because I mean. Let me pull up the formulation again. All right. So if you look at this formulation of the minimizer, then so I mean you're completely right. You could basically also put some sampling scheme into the negative examples, and I mean the effect that will have then really depends how you set up this similarity function here. So I mean I think in almost all the embeddings I think it's fair to say in all the embeddings that you saw in this talk, this distribution, like the negative distribution, does not depend on the reference sample, right? And it's just the empirical uniform distribution around across the data set, but that doesn't has to be like this. So what you can, for example, do is, if you want to become invariant to a particular latent variable, you could think about a sampling process where the distribution for that particular variable then cancels out in the denominator and the denominator. So we do this, for example, there's one mode in Zebra where we have different animals, and you train a joint embedding space, and you want the embedding space to become invariant of the animal. So then you would, I mean, again, it's very straightforward. So then in the positive and the negative samples, the animal ID is sampled with the same distribution, and then it cancels out. And so that's a simple example. For the group case, happy to chat more if you have ideas in that direction. What would be, yeah, no, but I mean and the ideas is very, very good. So you can definitely use the negative distribution to also shape properties of the embedding space. Yeah.
And what do you think? What is more critical choice? The positive sample? Or
The positive.
The positive, more
Yeah.
topology of the latent space.
Yeah. So the yeah. So I mean, it depends a bit on your family of distributions as well, right? But it's maybe for the I think we can chat offline. But the negative distribution is more sort of an so what can become a problem actually is if your data distribution is not is not uniformly distributed, is very peaked or something. So then you can potentially take measures in the data set, resampling to a certain degree to make it a bit more well behaved. But yeah. Yeah.
All right. Thank you very much once again. So what we're going to be doing now is, because we didn't have the time to do it before, so we're going to have 30-minute break. But it's not really a break. It's for all of you who got a poster to go there, stay there. And now these guys will go there and complain about your work, right? Just for 30 minutes, and then we come back, okay? So 4:15, we start off with Rui, okay? Thank you very much. right, let's make a start. You ready? Yeah? All right. Israel. Hey. Okay. All right. Very good afternoon again. Last session of the day. For that, we've got Zhang, I believe. I tried to pronounce the best I could. He is a PhD student at the Optima Group at the City University of Hong Kong. Rui holds a very special title in this winter school. He is the youngest presenter of the entire school. But do not get fooled by him being young. He's probably the smartest here, because while you are trying to basically find the prompt that will be making your papers, he's actually creating the algorithm that will make the prompt to finish his PhD. So basically, he's not going to do anything at all. That's the whole thing, I believe. But he will anyway make it. So please show us, take us away. Thank you very much, and the floor is yours.
Thank you very much. So I find the speakers here are famous supervisors and professors, so I'm a little bit nervous here. So I'm more than honored to be here on behalf of my research group, to present our recent work on the topic of the automated algorithm design with large language models. So my name is Zhang, and as just what SXS, I'm from the Optima Group from the City University of Hong Kong. And I would like to start by a brief introduction to my school and research group. So our school is the City University of Hong Kong and located at the Hong Kong Special Administrative Region in China. But I live in Shenzhen, so I have to travel from Shenzhen to the Hong Kong by subway every day. So our group is called the Optima, and we have, so this group is led by the Professor Zhang, who is dedicated in the optimization, and Dr. Zhi-Hua, who is my supervisor. We have more than 20 PhD students and postdocs and research assistants. So this is our homepage, and you know the QR code also take it there. Okay. So let's talk about today's topic about the algorithm design. So you know the algorithm design plays an important role in various a diverse set of application scenarios like port scheduling, warehouse scheduling, and chip design. So performing the algorithm design is not that easy, because traditionally we at least have some research scientists to do some theoretical analysis and came up with new ideas, and a programmer to implement that ideas into code, and maybe an engineer to deploy the code into the real world industrial scenario. So this process is like a labor-intensive process, and it costs a lot of time, right? So this really motivates us to introduce automation in this process. Like if we can introduce some automation, we can speed up the innovation and ideation, right? So let me quickly walk you through the outline of this talk. So I will first introduce some background about the algorithm design, and I will introduce you a subset of our recent progress in this area. And if the time permits, I will show you the platform and demonstrate the Jupyter notebooks. So this is about today's talk. So let's get started. So how do people perform automated algorithm design prior to the era of large language models? So one common method is called the hyperparameter tuning. We take the NMW as an example. So in this optimizer, we have some key parameters like the beta 1, beta 2, which controls the decay rate, and like the eta controls the learning rate, right? So these are some hyperparameters. So the goal of the automated algorithm design is to search for a combination of these 3 parameters or some other parameters to make it have good performance in the downstream tasks. Okay, so we can use some existing optimization techniques like random search or Bayesian optimization or something like that. So So this kind of search method can improving the efficacy of these algorithms. However, no matter how to combine these parameters, the algorithm is essentially the same because the idea behind the algorithms are similar, right? Another prevalent method is called the genetic programming. So in genetic programming, the algorithm is like just represented as a symbolic trees. So there are nodes in the trees and some terminal nodes. And it can be parsed into a kind of program based on some rules. So in genetic programming, the new algorithms is obtained by some evolutionary computation operators like the crossover, as shown in this GIF. So the better algorithms are created by exchange the subpart between these trees. So there is a paper called AutoML0 proposed by the Google, and it uses this genetic programming to find some really informative algorithms from scratch. So although these kind of methods is flexible and intuitive because every node is visible to us, so it's very explicit and interpretable. However, it's really difficult for other people to define the primitives before the search. So it's just really an expert-driven process. It's essentially an expert-driven process because we don't know how to use these operators in a specific task. Therefore, despite the long history of the existence, so genetic programming is not very popular in the realm of the automated algorithm design. So then come to the era of the large language models. So if you can see the timeline here, the y-axis indicates the code generation capabilities of the large language models, which is higher the better. And so these days we have witnessed exponential growth of the code generation capabilities. So this has significantly changed how we do automated algorithm design. So in the era of large language models, we can simply input our intention and something like the task description to the prompt content, and we send it to the LM. And then we wait for the response, and then it generates some code, and we can subsequently evaluate the code and get the performance. So this step can be repeatedly performed for many times until we are satisfied with the performance, right? Okay. So the advancement of this large language model also raises an interesting question that, so is letting LM try many times sufficient for automated algorithm design? So to answer this question, we have performed this experiment. Okay. So the x-axis is the number of trails or number of queries to the LM, and the y-axis is indicated by the performance gap to the best known algorithms. Although it's lower the better, and each box indicates the performance, the distributions of the performance of top 5 algorithms designed by LMs. So the lower the box, the powerful the algorithms. So we can observe from this figure that if you can see the lower bound of this box, we can find they are they're converging at a very low speed, right? So so simply letting an LM to try many times is very insufficient, even if we try 100,000 times. So how about integrate the large language model with a very simple search method? So how it happened? Okay, so this is a very simple search method. So in this method, every time we interact with large language models, we provide the best algorithm found so far during the search, and then we let the LM generate a new one inspired by the best algorithm found. We can find that we only use about 500 samples, and we can find the performance can match that of the standalone LLM at about 100,000 steps. So it's very surprised, right? So this observation reveals that integrating LLMs with the search method is very important for AD. And another interesting question is that what happens if we use more powerful LLMs? So we did this experiment. So this work is done like in early 2024. So the GPT-4 is the most powerful LLM we can get. So here is a result, and the result showcases. Something I forgot to tell. So this region is a code LLM, which means they are fine-tuned on the code snippets, and these are general purpose LLMs. And the color of these LLMs is indicated by the performance, and is closer to the red, then it has a higher performance. And we can have a conclusion based on this observation that, even more capable LLMs does not necessarily promise a better performance, because even if the Cloud 3 OPUs is slightly higher than the GPT 3.5, and even the very small LLMs at that time called StarCoder, which is proposed by the Microsoft, is a code completion model. Okay. So based on the two experiments, we can draw some conclusions. So the inherent generative capabilities of large language models alone is not sufficient for AD. And it holds true when we have many query budget and even we use more capable LLMs. And the good performance in this experiment, like we combine the search method with LLM. So this experiment, it suggests the necessity of coupling LLMs with a search strategy for AD. And in this work, we use evolutionary computation. In this talk, we talk about some integrations for the evolutionary computation. So we have abstract the paradigm into, we have abstract this kind of system as a paradigm, which is called the LLM-based evolutionary program search, abbreviated as EPS. So we have in this paradigm, we have an initial population. So each population consists of multiple individuals, like a code, executable, sorry for my job, executable code, like Python code or Java, whatever. And there is a search process and running a loop. And in this loop, we iteratively perform this kind of process. So we first perform selection, and we select good algorithms founded before, and we let the LLM to summarize a good experience while designing these algorithms, and let LLM to generate a new one inspired by these examples. And so after obtaining that new algorithm, we just evaluate its performance and send this algorithm to the population, send it back to the population, and we can iteratively do this. This is a basic paradigm of how to integrate large language models with the search. Okay. So as a conclusion, the algorithm is represented by executable computer programs, and the new code is generated by the large language models. So this is a roadmap of this area. So about in late 2023, so our work is to use the algorithm evolution pipeline, and we built the human-designed GLS method, which is the guided local search method. So even in 2024, we can beat human-designed method. And later we have proposed a paradigm called evolutionary of heuristics. So and after we have extended this method to a multi-objective version, it is called the multi-objective EOH, and some other works. There are many simultaneous work which like this. Fun search is proposed by the Google DeepMind, and the paper is accepted by Nature. So this work they use LLM to solve many mathematical problems, and they have achieved a lower bound or a never founded algorithm, which is very interesting. So and there are many other applications like this. The Disco POP, which uses the LLM to design the preference optimization algorithms. So if you know, there is a well-known RL library called the TRL, which is Transformer Reinforcement Learning. It is developed by the Hugging Face community. So this code POP is integrated in that library. And recently there is a method called the Alpha Evolve, which is also proposed by the Google DeepMind. So the Alpha Evolve has achieved many astonishing results, and they have applied their method in their Google server and in some other real-world applications. Okay, this is a simple roadmap of this area. So let's talk about some methods. So first, I would like to talk about the paradigm of evolutionary of heuristics. So this is the first paradigm that synergistically combine the large language models and the evolutionary computation. So in this kind of paradigm, the large language model is acted as a designer, and the search engine is going to maintain a diverse set of solutions to evolve, to guide the search, right? And in evolutionary of heuristics, so the key features of this method is that we not only evolve the code itself, but we co-evolve both the code and the ideas behind the code. And we use some operators like that is like E1, E2, and some modification operators like M1 to M3. So this is a very simple operator. Like we select several algorithms with their ideas and their code implementations, and we feed this algorithm to the LM, and we tell the LM to generate a new one based on this experiences. So we can iteratively do this, and in the evolutionary loop, so at last we can obtain a solution set that consists of many good algorithms. So this is the key features of the EOH. Okay, so in the EOH, there are some advantages, like we don't have to fine-tune the model because we can leverage the in-context learning capabilities of the recent large language models. And the evolutionary process provides the open-ended heuristic discovery. And since we are co-evolved thought and the code, so we can not only obtain good code, but also we can obtain insight from the code, right? So here I want to show you a case study. So this is a problem called the online bin packing. So in the online bin packing, the specification is that so we have a set of items, and our goal is to pack these items into the bins, and our goal is to minimize the use of the bins. The lower the better. And there is a word called online, which means once the item is put into the bin, then it cannot be moved. Okay. So this is a like a robotic arm to pack these items. And let's see some human-designed heuristics to pack these items. So this is our box, and this is the items to be packed. So we first, we simply put the item to this box. So this is kind of simplest solution. We just put the item to the first box that has available spaces. And here is a better one. So let's see how does it pack. So we find that they use a fewer box than the upper one. So this one is better than the upper one, right? And we can use, so in this problem, we can use the number of the bins used as a performance indicator. So we can make it lower the better. And this is like a discrete optimization problem. So this slide shows you how EOH solves this problem. We let EOH design a priority function. So this priority function controls which bins an item is assigned to. So we just let the LM to design this function. We provide the doc strings and the specifications of the problem to let LM know how we are going to do, what we are going to do. After obtaining the new algorithm, we evaluate the algorithm in multiple problem instances to make sure it is robust. And the final performance score is aggregated over the performance on these instances. So this is an example of the evolved algorithms for EOH. Okay. So a little more. See that clearly. So in this figure, so here we demonstrate the evolution. This is not a little bit vague. So this figure shows how EOH find novel ideas during the evolution. So this algorithm, in these algorithms, it adds penalty for very large bins, and like in this algorithm, it's aggregated over some key parameters and perform a weighted average. So these are new insights obtained from the evolution research. So this is, and this figure is, and this algorithm is the final algorithm which has the best performance compared to the existing one. Okay. And there's a table showcasing the final result. So EOH achieves better result compared to FunSearch, which is a strong baseline and some expert-designed heuristic like best fit and first fit. We have applied EOH to some other combinatorial optimization problems, such as traveling salesman problem, and EOH also outperforms the existing method, and this is unusual combinatorial optimization problems. And some other combinatorial optimization problems, like the FSSP, which is flow shop scheduling problem. And we use EOH also in some machine learning scenarios, like we use EOH to design the acquisition function for the Gaussian process, and the EOH also achieved the SOTA result. And we also let EOH design a generate function to obtain an adversarial image to in the kind of adversarial attack problems. And recently, there is a very interesting problem called the circle packing problem. And we find that EOH has achieved a world record like this. So this is the best known algorithm designed by human expert, and this is the alpha evolve. So it is better, a little bit higher than the best known algorithm. And this is a company called Fico, and Express is a solver. Okay, so EOH is outperformed than this method, and note that the EOH is open source, which could be important in this area. Okay, so this is all about EOH. And next, we will talk about the multi-objective version of EOH, because in real-world scenarios, the algorithm design is naturally multi-objective, because we not only want our algorithm to be well-performed, we also want it to use less computational resources, or we want it to run very fast, right? So this is sometimes some conflicting objectives, and how to perform trade-offs between these conflicting objectives is a key problem. And MEOH addresses this by introducing the multi-objective search into the EOH pipeline. And finally, we have achieved good result. Like compared to EOH, the multi-objective version has a higher hypervolume and a lower IGD score. And we have so the performance of the EOH and the MEOH is here. And we have tested it in some combinatorial optimization problems, like the online beam packing as we introduced before. So this slide shows the parallel front of the search algorithms. So we can find that there is indeed some method has very good performance, but they are very slow, and there's very not so good problem, but they are increasingly fast. So sorry. Okay, so these methods are searching for, these methods, MEOH and EOH are searching for one single algorithms. However, in real-world scenarios, we want to have more algorithm to cover many problem instances. So to address this, we propose the EOHS. So instead of designing the optimal algorithms, so we design a set of algorithms to enhance the complementary performance. This is also an extension of the EOH. So to do so, we use the idea of the few for many. So this is also the paper in iClear. So in this few for many settings, we want to use less solutions to cover many instances, like the solution 1 can cover these instances, and solution 2 can cover this. And they're complementary solutions, so this set of solutions can cover all the instances, and this is our goal. And there are plentiful of experiments, so we can find that the EOH is outperformed than others in many instances and many problems. Okay. So this is a very interesting paper recently been accepted by the IVR. And so this is called the multimodal LES, so which means we integrate the multimodal into the EOH pipeline. The motivation of this work is that we want to use the multimodal LLM to summarize the behavior of these algorithms, so to further assist the algorithm design. Okay. Yeah. So so this is a more complicated evolutionary loop compared to EOH, but the central are essentially the same. Like we have a evolutionary loop, and there are some more complicated modules like the summarizer and something like that. So the role of LLM is not only to generate new algorithms, but only to summarize the behavior of the algorithms. So we can perform a reflection based on this summarized content, and then we can further improve the algorithm design. So this is a case study of the MLES. We found that this is a traditional EOH pipeline. So this is in this problem, we want to control a car, and the function is an action of how to control the car. So this here we found an unexpected, like a spin here. But after we use the MLES, we make this frame as a content, as a behavior, and we input it to the multimodal large language models, and we refine the algorithm. Then it like this. It successfully knew the problem. And this is another example. So I don't know why the picture is very weird. This is like a spaceship. So the function is to control the posture of the spaceship, and the final goal is to control this kind of spaceship to land on the moon. Yeah, so this is an example of how the MLES control this kind of spaceship. So the last method is called the behave sim. So this, we are not going to introduce a new method, but we are looking back, and we want to see how to measure the similarity between two algorithms. So the motivation of this work is that, an increasing number of algorithms are AI generated or AI assisted. We are wipe coding every day. So the challenge is that how to automatically distinguish whether an algorithm is essentially different from others instead of a syntactic refinement. So this is very important. So we want to define the algorithm similarity and to measure the similarity in the code level. So we have an example here. Can you see these two algorithms, the code? So these two algorithms are the depths for the search, and these two algorithms are, so this is the BFS and this is the DFS. I think you know that. The only difference in code between the BFS and the DFS in the iterative implementation is that this function has a parameter of 0 and this is empty. Okay, so these two iteratively, in the iterative method is very similar in the code space, and there turns out to be similar in their abstract syntax tree and their token. However, this is a recursive implementation of the DFS, and these are same algorithm, but they're not very similar according to their AST score and the token score. So this is not very intuitive because these are essentially the two same. These two algorithms turn out to be the same one. Okay, so we find that simply measure the similarity between the code space is not enough to measure the algorithm similarity, because algorithm is more complicated and has more semantic stuff. Another solution is that how about we focus on the output of the two algorithms to distinguish whether they're similar, and obviously is not. This is not okay, because like we have an insertion sort and a bubble sort, so we have the same input, but it has also have a same output, but the internal step of these two algorithms are different. But so we cannot focus on the final output to say whether these two algorithms are same or not. So these two examples indicate that we should analyze how they behave in problem solving when measuring the algorithm similarity. Another example is shown here. so this is two algorithms, and this is their behavior. This is like a traverse problem, and the difference of these two algorithms lies in the argmax and argmin function. And surprisingly, their data flow graph and abstract syntax tree differences, similarity is 1.0, which means they are similar, they're identical in these two perspectives. However, these two algorithms have quite different kind of behaviors, so we cannot just measure the similarity in the space of the EST and embedding and also the token level. So they are not very intuitive. But we can measure the similarity in the, in the behavior level, because these behaviors are distinct from each other. So this motivates us to propose a new method. So to further verify this, we have created a data set consisting of 4 types of data. So the cross mark means that they are very similar. These data are similar in this level, and the cross mark means they're not very similar. So we have proposed a data set, and we compare our methods with existing code level similarity methods. So we find that they are not capable of measuring the behavior similarity of the algorithm, but our behave sim can do it. And our key ideas of this is that we just simply represent the behavior of the algorithm into the problem-solving trajectories. So what is a problem-solving trajectories is like this. This is an optimization problem, and each blue point is a solution. So the problem-solving trajectory is a sequence of intermediate solutions. Okay. And how to measure the similarity between two sequence of problem-solving between two problem-solving trajectories? So we can use many methods that is used for measuring the trajectory distance to apply it for the behavior difference. Okay, and this is the equation part. We use the DTW distance because it can handle the time shift, and we can skip this. And we perform a normalize to make the similarity map to 0 and 1. And at last, the behavior similarity of two algorithms is finally aggregated over multiple problem instances and starting point. So here we show an example of how to measure the behave sim. So we have 3 kind of optimization methods like the SGD, BFGS, and conjugate gradient. So we can find that the trajectory of these 2 kind of methods is similar than these 2, right? So this can be indicated by the higher similarity score, and this has lower similarity score. So from this plot, we find that behave sim aligns with our intuition. And another example is here. So we can find that the algorithm 1 and algorithm 3 is more similar than the algorithm 1 to algorithm 2. So we can find that the behave sim, so this value is higher and this value is lower. So this also aligns with our intuition. This is all about the behave sim. But the question is that if we have a metric that can measure the similarity of 2 algorithms, how we can use it for the automated algorithm design. So our solution is that we try to encourage behavioral diversity in the LM-AAD process. Okay. So we use the backbone of fund search pipeline, where we have a database consisting of multiple islands, and each time we perform selection and generation process, just like the evolutionary computation, similar to that, very similar to that. And in the island, we cluster algorithms with similar behavior similarity, with similar behavior to one cluster. So this is like a niche-based integration, so that we can increase the diversity of the entire population. And this turns out to be highly effective. And we have tested 3 problems: a mathematical problem, a combinatorial optimization problem, and also a CO problem. So we find that our method is highly effective by promoting the diversity of the population, especially the behavioral diversity. So another case is that we can use this method to some algorithm analysis process. Like we perform a case study like this. Like we cluster the algorithms founded by the fund search using the and we get the final data. We get the final database checkpoint, and we find 30 algorithms, and we cluster them using 2 kinds of similarity metrics. So one is our behavioral similarity, and the other is the code blue, which just measures the code level similarities of 2 methods. Okay, now okay, we find that there is some algorithm similar in the code blue, but just very different in the behavior, and vice versa. So what does this? So why was that? So we have a case study, and we find that algorithm, and we try to analyze that. So we find that sometimes this is caused by a different calculation method of the final score, and sometimes it is caused by a bug of the large language models. So this makes the behavior to be similar, to be identical. And this is all about the behave sim and this work. So the paradigm of EOH has also been applied to other interesting scenarios. To tell the truth, I'm not very familiar with this scenario, but it's like one of my friends to do this. So they are designing the physics model, and they achieve good result using the EOH pipeline. And another friend of mine, he just used the EOH to design the shape of the wings in the aeroplane. Like this is the wings. Okay. Yeah. So this is a recent work of our group. So they have used the EOH to assist the acceleration of the CUDA kernel. You know the CUDA kernel. So if you use the torch, you may have some basic kernels like the matrix multiplication. So the goal of the CUDA kernel optimization is that we want to adapt the CUDA kernel to different hardware architectures, like there's a Chinese company called Huawei, and they're an AI chip. So we want to apply this kernel on their devices, and we perform acceleration. So they also achieve good results using this kind of pipeline. They have as much as about 30 times acceleration, 30 times speed up. So this is all about the method and applications of the EOH pipeline. So do I have time left? Okay, so here I want to share you a platform. This platform has integrated these algorithms I have just introduced. So in the platform is in this link and this QR code, and it's called the LM480, and it's about maybe 500 stars now. So in this pipeline, we have integrated these methods, and we have support many large language models, and we integrate as much as more than 100 tasks, AAD tasks, and we are also we have some tutorials and GUI and docs. And we are gonna update this platform to V2 version recently. And this is a demonstration of the docs, the documents. And this is an experiment performed using the platform. And this is some other results. And using this, the API of this platform is quite easy. Like we just import these necessary modules and we just add our API keys and tell the system to use which method and to use which task. And then we use the .run method to start the experiment. Yes. And this is a GUI. So this is a preliminary version. We have a more beautiful version in the V2. Okay, so now I have a Jupyter notebook to show you how to run this. I don't know if I can access to the API because I use a provider in the API provider is in China. I don't know if I can access to the API.
But you need to put your camera.
Oh, so they're not. The screen is not synchronized.
It's not duplicated, no.
Oh. Oh, yeah. So I will not run it. So there are some logs here. So this is the Jupyter notebook. So I have uploaded this Jupyter notebook in my GitHub account. So if you are interested in that, you can search for this account called. The internet is not so fast. For this, Razy HHH, Razy triple H. Oh. And this is my. So I cannot see it here because I have signed up to my own account. Oh. Oh, can I start here? What? Sorry, wait a moment. Oh, I find it here. So the project is this the GPA Jupyter. So I have uploaded the Jupyter to this GitHub repo, and it shows how to use this platform to perform an algorithm design. So in case you are interested, you can download this repo. And this API is fine for use, and the API is expired in about 1 week. So, okay, I will not run it. Sorry for that. I don't know why. So this is all about this day's talk. So finally, I want to have a try. Why this cannot help? Python environment. Oh, I forgot to select a Python interpreter. So in this Jupyter, I tell you how to design an algorithm for the traveling salesman problem. And in this folder, I have also uploaded the slides about this, about how to, what is this problem, the setting of this problem, and some and how to design design a template program, and to evaluate the program. So this is in this slide in the folder. Okay, Okay, and the API is quite easy, but the evaluation can be complicated. We just, like here, we just import these packages and we create a new instances and just run. So I'll skip this. So, so in this talk, I have introduced you a new paradigm called the EC plus LM. Like, it's very powerful to synergistically combine the evolutionary computation with large language models. And I also introduced some recent advances in this area and our recent progress in this scenario, in this kind of research area. And I also put the QR code of our platform here. And this is all about the talk. And thank you very much. And if you have some questions, you can tell me. Thank you.
All right, time for questions. Carlos, go for it.
This is a quite interesting way. This is like taking our jobs, isn't it? No, sorry, Steffen. So my question is about the population initialization. So how do you, for a specific problem, do the population initialization of the genetic composition evolutionary algorithms?
Would you please come again, please? My English is not so well for listening. Sorry about that.
What I mean is, how do you initialize the population of the evolutionary algorithms?
How to analyze a population in
initialize? How to
the initial population?
How to get an initial population?
Yeah.
Oh yeah.
How did you initialize it?
So we can use some expert design examples for initialization, or we just let the LM to design some algorithms, and we just preserve the feasible one to as the initial population. Yeah.
What if there is no feasible algorithm in the population?
Yeah, this can be really hard. This is a very good question because I really meet this in some very hard problems. And so I think maybe we should fine-tune the prompt to give it more information about how to design a feasible algorithm, or we just use a more powerful LLMs like sometimes I use the GPT 5 Nano, it fails, but I use the Gemini 2.5 Pro, it's success. So this is two kind of ways.
No, so thank you.
Thank you.
More questions, please?
Yeah, I have two questions. One is more practical about the platform. Can you use open source LLM like local ones for the platform, or you have to apply the API for the Opus and ChatGPT, or?
Okay, you can use the open source one. You can deploy it locally using either the SGLang or VLM or some other inference libraries, and you can once you can tell the system how to access the LM, it works. Yeah.
And another question is, for example, for the problems as a traveling salesman, which are kind of famous, and you have a lot of solutions already, a lot of algorithms available in the literature. Have you tried to analyze whether LLM takes somehow generates solutions which are similar to already published ones, or are they coming up with the novel algorithms?
Wow, great question. So we not have done this yet because this is a very labor intensive. We have to see its algorithms and to do this. But recently I have performed an experiment, but not shown in this slide. So we similar with this one. Yeah. So we perform some clustering to existing algorithms and compare it with the algorithm designed by the LMs, and I perform the clustering. So I find that there are not so many insights I can obtain from this experiment, but I found some algorithms designed by the LM is highly similar. and also the behavior aspect, the behavioral aspect of the expert design algorithms are also similar sometimes. Yeah.
Thank you.
Thank you.
You maybe need to use contrastive learning to represent every algorithm, and every point that is really close, you have a look, and so it's not so labor intensive to check whether it's novel. At least the point is farther from existing solutions.
Nice
Yeah,
idea.
cool. Sounds great. Any other question? If not, it's Friday, almost Friday evening, so we're gonna thank our speaker Rui once again. Thank you very much.
Thank you.
And that's it. Thank you again. For those of you joining for the tour tomorrow, please let us know. We posted a poll on Telegram. Please do say yes if you're coming. If you're not coming, well, I'll see you probably Monday. But tomorrow and Sunday, we might be around. Please use a chat if you want to go for, a beer or 2 or 3. I would be happy to join. All right? Thank you very much. See you later, guys.